Hello. There we go. Good morning, everyone, and welcome to the final day of the CAMS Global Assembly. This morning's session is on atmospheric composition, and our first speaker is Johannes Fleming, who's going to be talking about the CAMS global system. Morning, thank you.
Thank you, Melanie. Good morning, everybody. Yesterday, we had the chance to test two varieties of olive oil. Today, it's two varieties of the IFS. I hope you enjoyed at least as you enjoyed your olive testing yesterday. So I'm talking now about the IFS, the global CAMS system. And this is development work, a joint effort of many, many people. And listing these people always has a problem that you forget about someone. So apologies in advance. The global CAMS system is developed by people at ECMWF. It's run by people at ECMWF, but we also have many contributions from external partners, and we also have the evaluation efforts as part of CAMS that look whether the results of the global forecasting system are improving. That was not the slide I was hoping to show. Well, if I press next, then not my next slide comes up. Thank you. So this is a reminder of our CAMS infrastructure for our global forecasts. We have the emission data, we have data for the assimilation, and there are two systems, the regional system, which was the focus yesterday, and the global system, which is the forecasting system of the IFS, and that's what I'm talking about today. Could you make the next slide, please? The green button? That's what I do. Okay. So the global CAMS system is the integrated forecasting system with modules for atmospheric composition, for aerosols, chemistry, and greenhouse gases. Aerosol and greenhouse gases are referred to as COMPO. So that's also not the slide, but it's fine. It's fine. An IFS COMPO is aerosols and chemistry. GHG is, of course, GHG. And we are very much interlinked in our development with what is done for the numerical weather forecasting. So many years ago, we decided that for the upgrades of the CAMS system, we exactly follow what is done for the numerical weather prediction system. So the timeline of the upgrades is dictated by our colleagues from NWF for the numerical weather prediction. Could we have the next slide, please? Yes. And this preparation of those upgrades is a relatively complex and long-lasting procedure. So that's why I want to briefly run through the points 1 to 4 with you. So first we have the step where the individual partners make their developments of certain features of the IFS, which they think will improve the forecast of atmospheric composition. And then we have the important stage where everything is put together. And one aspect of this putting together is that we have a code review procedure now in place. So if external developments, also developments from in-house, are meant to be included in this big software package, which we call the IFS, people inside, colleagues will review and make sure that they are in line with what we do in terms of coding standards in the general structure. And then once everything is put together, we have to test all the different changes coming from the developments for the atmospheric composition, but also coming from developments from the weather forecasting together, and to test them. And also at this stage, we start with the testing for the data assimilation, which is sometimes difficult to do before, and very often also the final decision, what kind of emission we are going to use, is done only at the stage when we do the integrated testing. This process usually takes half a year, and once we are ready, we start what is called an experimental operational suite, so the E-suite, and this suite then is started in terms of the start date about 9 months before the actual implementation date. It runs in catch-up mode and then in near real time, and at the point of the implementation, we switch to this experimental suite and say that's the new O-suite. So that's the procedure. There are two messages here that it really takes quite a long time from the development stage to the operational implementation. This is maybe helpful for some of you to understand why we are sometimes not so responsive. And the other thing is that certain decisions, like what emissions we are going to use, that they're usually made at a relatively late stage, even though in theory we would have needed to do them early on if we wanted to follow this general procedure. So there's always time pressures, but we cope and we try to make the best of it. And so we are now looking forward to the implementation of 48R1 on the 27th of June, and the GHG suite will be implemented in Q4 of this year. Next slide, please. So one of the main innovation of 48R1, which is really a very, what we call a big cycle, where we change a lot of things, is that we now for the first time simulate stratospheric chemistry using the VASCOE scheme. And I think Quentin will then in the next talk provide you with more details about this. But this is not the only addition in terms of new variables. We also added two aerosol representations for secondary aerosols into the IFS. So if you're interested in the aerosols, you really need to make sure that you also download the data for the two species for secondary aerosols. The tropospheric scheme was also extended, and we now have glyoxal, because there was a request from the retrieval community that we should provide forecasts for glyoxal, which they could in their retrievals. And we also now include HCN, which is a tracer of biomass burning, which also has implications for infrared retrievals, so we thought it's an interesting addition. A general restructuring of the emission took also place prior to 48R1. And this gives us the opportunity now to model in more detail on a sector-by-sector basis things like diurnal cycle and the injection height. And finally, I also want to say that we have a new photosynthesis model in the IFS. Next slide, please. This is now a much longer list of additional developments, and they are not minor. I don't have the time to go through all of them here, so it's just for reference. Maybe I just wanted to mention that the dust modeling has been considerably changed, resulting in much higher burden of the dust for all three bins. So again, if you're using the global data, you may want to be aware of it and test your use of our dust as boundary condition. In terms of the data assimilation method, we also had some updates. Maybe it's worthwhile mentioning that now, because of the correction of some error, also the nitrates and ammonia is directly influenced by the data assimilation, something that did not occur before. And in terms of the satellite retrievals that we assimilate, we usually don't follow the same procedure in the updates like for the cycle. So new satellite data are ingested in the system also in between cycles. So worth mentioning is that we are now assimilating VIRS, AOD, but we already started this with the current O-suite, and we also have an addition of the carbon monoxide from TOPOMI, which is also assimilated already in the current operational system. Last point, very important one, is that we also work very hard to document what we do. So for the first time, there's a comprehensive documentation of all the scientific aspects of the atmospheric composition in the IFS, which will be published together with the other parts of the description of the IFS, which focus on aspects like the physics and the numerics and so on. Next slide, please. Thank you. The VASCOE scheme, I mentioned it already. It's stratospheric chemistry for the first time, and in the next talk we will hear more details. So I just wanted to say that we are adding now 64 species, so it's basically doubling the number of chemical species, and this also leads to a considerable increase in cost by a factor 2. So it's really quite expensive. So we really have to think, why are we going to do this? And I think there are a couple of benefits which are not just improvement in the scores, but really the prospect of doing more in terms of the stratosphere. So we have now stratospheric species which we could in the future assimilate, so this prospect is now there because of VASCOE. We also have the possibility to actually simulate processes like the loss of methane in the stratosphere, which is interesting from a methane perspective, but also from a water vapor perspective for NWP applications. This is also now possible. And I think the most important point is that our monitoring of the ozone hole is really improved. So far, we can say, well, we can show the symptoms. We can show the ozone hole. That's here. That's one of these cross sections. It's just a snapshot from the year from October last year, where we see the ozone hole over the South Pole. And what we also showed so far is sort of then the corresponding temperature fields and trying to explain the development of the ozone hole from a dynamic perspective. But now with Basque, we can also show chemical species that are involved in the rapid depletion of ozone, which I think makes our efforts much, much better. Of course, it also raises science questions, but it gives us a new dimension for looking into the ozone depletion. So I show here HCl and ClO as a sort of marker of the activation of the chloride. And it's really nice to see this correspondence with the location of the ozone hole, the ozone destruction, and the occurrence of these species. There is also a benefit just in terms of ozone itself. In general, we say the ozone fields are not improved in terms of the analysis and also of the forecast in most cases to what we had previously. But there are exceptions, and this exception is also the ozone hole. The current scheme, HLO, is really, is sort of, broadly speaking, a relaxation to the ozone from the CAMS reanalysis, which works very well, but in situations where you have a very strong deviation, this doesn't work so well. So what we see here on the left-hand side is our ozone profiles in red from the current O-suite, and in blue what we are going to implement at the end of June. The solid curves are the analyses, and those two curves, the arrows here shown over Antarctica in October, they are relatively similar. So in terms of the analysis, and because it's all constrained, we don't see so much of a difference. But if you look at the 5-day forecast, which is the dashed line, we really see that with the current scheme, we have a much larger increase in the bias after 5 days than compared to using the proper sort of chemical scheme. And the plot in the middle shows a similar aspect. What we show here is the RMSE error against the own analysis for the 5-day forecast over Antarctica. The red curve in this plot is now the new version, where we have lower RMSE, especially during the time of the ozone hole, whereas during the duration of the ozone hole, the RMSE error in the current system goes up for the day 5 forecast. Okay, this was one example. What we see here now is sort of the overview of all the different updates, and they are judged in a scorecard, which is prepared by the external evaluation team led by Henk Eskes. What they do, as you probably know, there are many observational data sets which are taken to evaluate our global CAMS system for aerosols, for different chemical species, and if the scores of the 48R1 update are better, you will find green colors. If they are not, then you find red colors. So mostly it's green, so we are quite happy. 85% is an improvement or neutral. But there are also a few areas where the update is not an improvement, and this mainly relates to PM forecasts over areas like China. So let's have a closer look here. What we see on the right-hand side are the errors over the period 1st of September 22 to the 1st of March with 47R3, which is sort of the current system. We see we have on the sort of coastal stations sort of an overestimation. This is improved in 48R1, but on the more western side of China, the negative bias is increased. And overall, this leads to summary, it's a degradation. We think it's still acceptable because we have a global model. These are stations coming from different types of situations, urban, rural. So an underestimation of a global model is maybe perhaps acceptable, but of course we are trying to work on this. One of the positive examples is on your left-hand side, where we show NO2 forecasts over Europe from background stations. With 47R3, the old system, we had an overestimation, which is now much reduced with the new system. Okay, now moving on to 49R1. Again, we have a very long list of innovations which we want to introduce in this cycle. We are currently, in terms of the development, and at the stage where we merge all the different contributions, and we will start with the integrated testing. I'm not going through this list here right now. It's more gradual changes, so we don't have these strong changes as we had them for 48R1, but it may be worth mentioning that, for instance, for the optical properties of dust, we try to account better for the non-sphericity of the dust. We also expect better forecasts of the nitrate. There are also technical changes that the grip codes will be provided in a slightly different way, so you should be also aware of it. And we have plans to assimilate Sentinel-5P methane and OCO in the GHG suite. So it's a long list of updates, and this might not even be complete. For the emissions, we are heading for version 6.1, but this needs further confirmation. An important point is, however, that we intend, we are not 100% sure yet, increase the resolution of 49R1. 49R1 is an important cycle because it will also be the cycle which we use for the production of the next CAMS reanalysis. So the plan is to go to a 25-kilometer resolution when we think we can afford this. Okay, this is just one plot showing sort of giving a status update of the evaluation where we are at the moment with 49R1. What I wanted to demonstrate with those two plots is that people do developments, but then because of other developments, and in this case, developments coming from the ECMWF land use or land surface scheme, also the composition is changed, even though we did not intend it, or we were not aware of this in our own testing. So on the left-hand side, you see different curves for a one-year simulation of XCO over Park Falls. And if you just go from 48R1 to 49R1, as provided by NWP, you get a degradation, so additional tuning was required to get back to where we were before and to even improve on where we were. And on the right-hand side, you see a change in surface ozone purely coming from the fact that in the NWP part of the model, the land surface modeling has been changed, and we see average changes up to 5 ppb. That's all what I wanted to say. So the CAMS global system is the IFS. We have our development is ongoing all the time, but we stagger this in cycles. And from the discussions I had so far with many of you, I think this process of the preparation of the cycle, but also preparing users to the new cycle maybe earlier on, is an area which we could improve on or discuss in various groups in CAMS in a better way. Thank you.
Thank you, Johannes, for your very interesting and useful talk. We're running slightly behind, so I won't take questions now, but do feel free to talk to Johannes in the break. Our next talk comes remotely. It's Quentin Herrera and Simon Chevrolet from BERA. I'm hoping they're there, yep. So yes, the floor is yours. Thank you.
Can you hear me?
Yes, yep.
Excellent. I hope you are all going well and that you have a good conference. I will talk about the evaluation of the stratospheric composition in the next CAMS cycle 48R1. Yes. So why do we care about the stratosphere? Why the stratosphere did not attract much attention several years ago? There has been several recent unusual events, making it exciting from the scientific point of view, and certainly a matter of concern from an environmental point of view. On this figure, I show the trace gas and temperature anomalies for several species. And we see that in the latest year, there has several spots I will not mention all of them, but you see here the largest strong Arctic polar vortex ever measured so far. There has been 3 successive, very long-lasting Antarctic polar vortices with large ozone depletion, which have not been measured also so far. There has been the Australian New Year wildfires in 2020, which completely rebalanced the partition in the chlorine family, and which is something we don't understand yet. And then more recently, there has been the Ungatunga eruption, injecting a large amount of water vapor in the stratosphere. So there is, I think it's very good to see that CAMS now has a detailed stratospheric composition that allowing the scientific community to monitor these events. A very few words on the Basco system, a bit less than what Johannes expecting me to say. So the new cycle replaced the ozone linear scale with the Basco detailed stratospheric composition, which include around 60 stratospheric species with their gas phase, photolysis, and heterogeneous reaction. It has been described in the Aynan et al. Paper in 2016 with some updates done recently. And I show the scorecard on the right, and the green box show the region where there is some which are affected by this new chemistry. And in all cases, we have a green, even sometimes a double, a very strong green improvement. So in this presentation, I would like to evaluate the stratospheric composition, gas phase, and aerosols. It's a bit disappointing for the aerosol. I will discuss that a bit later, and some gas phases, and in particular, ozone, of course. This figure shows a comparison between EASI total columns in October 2022 against the E-suite. And we have on the bottom the difference between the O-suite and the EASI, and the E-suite and EASI. And we see that the E-suite really reduce the bias in the tropical region, in particular the one above the Pacific Ocean. Johannes already mentioned a better model to forecast the ozone hole. This is a comparison between the O-suite analysis and its control run. This is the comparison, and we have the same for the E-suite. And we see how the new chemical scheme allow to have a better forecast capability. And this is reflected, of course, in the 5th-day forecast, where we see that the O-suite still has a relatively important bias, which make difficult the forecast and the monitoring of the stratosphere during the ozone hole in CAMS. And right now, it's much better, so it's pretty good. Now we have done some comparison with real data, in particular 4 set of LIMS profiles from satellite instruments and the ozone sondes. The plots show on the top the normalized mean bias between the different, either the O-suite or the E-suite with this data, and each color is the difference between one of the data. So we have the bias on top, we have the standard deviation in the middle, and the correlation at the bottom. And the black line is the multi-instrument MIM, the multi-instrument mean, and what that we report here to make a better comparison between the O-suite and the E-suite. So we see below 10 hectopascal, I will come back to what's happening above, but below 10 hectopascal, we see a large reduction of the bias in the E-suite, which was in the past, in the O-suite has around 10% bias. It's almost negligible. And we are still talking about the 5th-day forecast right now. Standard deviation and correlation also increased greatly. So that's very, very nice. If we look in the tropics and again, the 5-day forecast. We see that the O suites degrade at some point the results where it introduced a negative bias of around 20 to 25%. And this is the so-called ozone model deficits, which is present in most of the stratospheric model. It lasts since several decades, and there has not been any solution found yet, as far as I know. On the other hand, if we go down below 10 hectopascal, we see how the E suites really reduce the bias down to 200 hectopascal, the one that was present in the O suites. The standard deviation are better and the correlation are also much better. The problem is that the O suite, in fact, the cycle 47R3 introduced an error in the setup of the B matrix when it has been introduced in October 2021. On this figure, we show the evolution of partial column of ozone between 70 and 100 hectopascal. From the O suite in red and the O suite analysis in red and its control in blue, and the BASCO near real time, which assimilates ORA-MLS, and we take it here as reference. And we see that when the cycle is introduced, there is a gentle drift that starts to become relatively significant from the middle of 2022. And then there has been a fix introduced in the cycle 47R3 last December that did a way to that correct it, but then there has been some weird things with the MLS data, but it corrects at some point. But we see also here how the E suite is really doing a good job. So basically, the improvement of the cycle of the new cycle in the tropical ozone it was more an issue of the configuration of the data assimilation system in CAMS than a model improvement. I would like to say a few words about stratospheric NO2 or NOx. In the past, we used to show this left figure showing the schematic GOM2 time series of NO2 stratospheric columns here shown in the tropical region, and how CAMS is red was enabled, at least from the recent years, was enabled to get a good agreement between with the data. And with the implementation of stratosphere chemistry, we could redo this plot here. We use SFTS data, so it's an occultation instrument with poor sampling and with the latitude bands which change slowly from day to day. So we see some large variation which are more due to the sampling of SFTS than natural variability. But we see that the agreement is much better currently. In fact, the new NO2 is overestimating by around 20 to 30%, and which would explain the ozone deficit that we discussed earlier. There has been this Onga eruption that injects a large amount of water vapor in the stratosphere. The eruptions occurred early in 2022. In this time series, which only focused the E suite period, so it starts in October 2022, we see that the water vapor observed by MLS has not yet reached the polar region. It reaches, in fact, only after the breakup of the Antarctic polar vortex. But now it's there, and it's not. We could not see it in the E suite analysis, and we check also if it was present in Q, so the humidity from the NWP. and it's not there anymore. When I say I mean the Q in the CAMS product, not for the operational meteorological product. So we're just wondering about the implication about the forecast of the ozone hole. I guess it will be a large impact for the dehydration of water, but it's not clear how it will be important during the ozone hole itself. I guess also that there is a radiative impact, and I think this is something that should be tackled in the next cycle, certainly. And then, last but not least, is a few words about stratospheric aerosols. I must say that these are very preliminary results. It seems I have some issues, maybe resolved now with grip retrieval. Everything was going very well with the chemical species, so I did not pay attention to the aerosols, but it seems there is some issue there, so I'm not sure my results are reliable. Anyway, currently, when we compare the aerosol extinctions at 4 wavelengths, which are available in the CAMS output, with satellite profiles, we see that there is a large underestimation, which probably means that the stratospheric aerosols are underestimated in the CAMS. So we have 2 satellite instruments. We have OMPS-LP and SAGE-3-ISS. OMPS does not measure at low at 355 nanometers. So to conclude, we have a new cycle with a relatively improved stratosphere with better ozone and NO2. We have many other species that have been evaluated, and I did not have the time to show all of them. But they will be available in the report that is currently under review. And there are still a lot of things to do. I think a proper evaluation of the stratospheric aerosol, also evaluation of stratospheric bromine, which have not been evaluated because there is no limb sensor measuring bromines currently. And then I think for a model development perspective, there is several issues about ozone deficit and stratospheric NO2, and also I forgot to mention the water vapor deficit due to the Hunga-Tonga eruption. And that's it. Thank you for your attention.
Thank you, Quentin, for showing some very encouraging results and some very interesting things to look at with the new eSuite. I'm afraid we're running behind, so there's no time for questions. But our next speaker is Samuel Remy from Hydios, who'll be taking a closer look at desert dust.
Okay, thank you, Mel. Good morning, everyone. So here we're back to the surface with dust. So in this talk, I will try to show how we deal with dust emissions and dust life cycle in the global model, which is not an easy subject. And so this is, of course, work done by the whole team and also in collaboration with CMWF and well, many other projects as well, which I would like to acknowledge here. So as you know, dust storms hit a lot of populated areas. I mean, over Europe, there were large events in 2022, 2023 as well, 2021. And it is more and more high in the media and also in general public. It receives much more attention. So this is one item. On the other side, what we do in CAMS, global CAMS, those products are used more and more widely by general users and also scientific users. This is just an example here of a study that we did with a Claire Ryder about how dust ingestions in the aircraft engines using CAMS dust data, for example. But there's many other work as such ongoing. So it's really a high-profile CAMS product, dust, like dust-related product, AOD, concentration, etc. So of course, we have quite a bit of pressure to improve as much as we can our dust forecast. So a quick word about how we model dust emissions in the global systems. So we try to represent some really small-scale processes, such as saltation and sandblasting processes, using a widely used parameterization, which is the Marti-Corona and Bergamatti 95, which is used in many of the models. and using Koch et al. 2011 dust size distribution emissions. Of course, there's many challenges with representing dust emissions. There's quite a lot of uncertainties about some, and if not all, inputs of the dust emission scheme, and in particular the soil typology. If we have sand, clay, or other types of soil, this is going to have a large impact on dust emissions, and this is not very well known over the whole globe if you have sand and clay everywhere. And of course, we try to represent very small-scale processes. The impact of those processes over a global 40 kilometer times 40 kilometer grid is quite a challenge, of course. Besides, we present dust in 3 size bins. So we can see here on the left-hand side, real dust, so silicates, calcites, dolomites. So it's really a lot of species with different shapes, colors, chemical composition. And right-hand side is what we try to do, so 3 assumed spheres. So that's a very large simplification. Of course, we have to do something like that for computing cost, because we cannot represent the whole variety of dust species. But still, it's a very large simplification. So what could we do to try to overcome the fact that there's such a difference between real-world dust and what we try to do? Overall, we try to follow 2 pathways of developments, and also in close we try to follow also what is done by the scientific community, because a lot of people are working on dust emissions and life cycle. We try to gradually complexify how dust is represented in the global system, as Johannes showed in some updates, for example, introducing new processes or some dust specifics. And on the other side, we try to develop experimental versions of the IFS, the Integrated Forecasting System, so the global CAMS system, that represent dust molecular composition. So this is not at all meant for operational use, but it's more to give us an insight, a glimpse of what kind of variety we have in the dust composition. And then that can be used later to provide information to the operational setup. So in terms of recent evolution of the dust modeling in CAMS, so this is just looking back and a little bit forward as well. In cycle 46R1, we implemented this new dust emission scheme, which was retuned in cycle 47R1. Cycle 47R3, which is the current operational scheme for still a few days, we've implemented some new deposition schemes for aerosols, dry and wet, which impacts dust, of course. Cycle 48R1 is quite a large cycle change for dust emissions, as mentioned by Johannes already. We have new optical properties and dust rebound, and also dust emissions have been retuned with quite large changes. Cycle 49R1, which we are working on currently, and which should be the cycle used for the next releases, is implementing dust asphericity in the optical properties and also a degree of hydrophilic growth. And finally, we're already working in cycle 49R2, so this is still ongoing work. And we are reviewing the number of dust bins, working now with 8 bins. That could be, this is not final, of course, and also working a lot on sedimentation. So this should be for 2025, but this is not sure yet, of course. So this is how dust should look like when in cycle 49R2. This is not sure, so it's a bit better. There's still some work to do, but we're getting there slowly, bit by bit. So when we compare different dust cycles, I'm not sure, yeah, this is quite visible. So this is just a quick comparison using very specific observations. We usually do evaluation of a long time periods, like a few years here and there. We also choose and pick specific events. So this one was the dust storm of 2022, mid-March 2022, the one that was shown by Leonor yesterday. Yeah, this is cut, it's not visible. So this was last year. And we tried to look here at PM10, focus over Spain, which was really the most impacted country, and Almeria in particular, because we have some grim optical particle counter observations there that was kindly provided by Elena. And in terms of PM10, you can see, I'm not sure if the color code is highly visible, but basically we do better and better from cycle to cycle. There's the operational, so 47R3 with assimilation, and also the other cycle, so 47R3 without data assimilation, up to 49R2 pre without data assimilation. And you can see that we are getting closer. We're still a bit far from observations in terms of PM10 over the whole of Spain, also over Almeria. On the left-hand side, you can see actually a glimpse of observed mass size distribution during this dust event as compared to simulations with 3 bins and 8 bins. So this is basically 49R1 in blue and pre-49R2 in red, and showing that we are getting also closer to observations and a better representation of a dust size distribution with the pre-49R2. In terms of representation of dust mineralogy, so this is very experimental. This is nothing meant for operations. So we followed basically work done by other people in the scientific community. So the work of Laurent Menu and this Scanza et al. 2015 paper. We use specific optical properties for each of the mineral species, which is very important because then this is going to tell us how absorbing or how extinctive is each of the mineralogical species. We use this dust soil composition from Journée 2014, and we try to evaluate against as many observations as possible. This was done by BSC in particular, and showing that we are in the range of what other models are doing. So these 12 species are shown here. I'm not going to list them all. So this is a much complex setup, and it is really quite instructive for the operational setup in terms of variety of dust mineralogical composition. In terms of evaluation, so our objective is really to try to evaluate as much as possible all aspects of a dust life cycle, because if you look only at AOD, for example, you will miss many things. If you look only at PM, you will miss many other things. So here, for example, we are using ground observations, remote sensing, fusion products model. We rely a lot on the DustCom, for example, fusion product. We are using deposition from remote sensing, ground observations of, AeroNet, PM10, of course, but also size distribution when we can. And we try to compare as much as we can against other models, because, of course, there's a wide variety of approaches in dust modeling. It's always good to compare against what other people are doing. So this is just an example here. I'm not going to go through all the evaluation we're doing. I mean, it will be very much too long. How we compare against a very nice merged AOD product that was produced by FMI. So this is, from this merged AOD, we derive dust AOD, actually. So this is on the left-hand side, this merged dust AOD at 550 nanometers. On the right-hand side, of the difference in forecast only for cycle 47R3 and cycle 48R1 from this reference data set, and showing that cycle 48R1, the difference is generally smaller. So we clearly reduce the areas with negative bias, in particular over Saudi Arabia or for transatlantic transport. So that's one such evaluation we're doing among many others. We are looking also at dust deposition, of course, because this can have quite a bit of impact for many processes in the ocean. And here this is showing basically dust deposition derived from MODIS and from MISR in bottom, and simulated on the left-hand side, also showing some climatological observation of dust deposition, and showing that, our simulated deposition falls in the range of what is given by remote sensing and also what is given by climatological observations. And for dust deposition, we also aim to use later products from the DOMOS project, which will provide some very useful products for this, such as deposition, which will be quarterly dust deposition. So that will be quite an improvement in terms of evaluating dust deposition. So to conclude, dust in the global system is really evolving from cycle to cycle. We try to follow, of course, an integrated approach. When we modify something, we need to look at everything else, and usually all processes need to be modified nearly at once. I mean, it's not easy. There's a lot of new remote sensing observations coming that are interesting, but one specific is about this soil dust mineral composition from the NASA EMIT mission, which we are waiting impatiently for the first results. And of course, it can be a bit hard to follow all of it changes from cycle to cycle, so don't be afraid to come to the CAMS 235 project if you have questions, also in addition, of course, to SIM2F. Thus, showing one last result, this result of simulated PM10, over the Southeast US. That was this Godzilla so-called dust storm in June 2020, which brought dust from Africa up to Texas and Florida. And we can see that we had difficulties in simulating the high PM10 values for earlier cycles, and that we're getting much better with this pre-cycle 49R2. So this is quite encouraging, let's say, for the future. Okay, thank you very much.
Thank you, Sam, for a very exciting and promising talk. I think we've probably got time for one question, if anyone... Do you want to... is there a... I think there's a microphone coming.
To me first? All right, it was me first. That's okay. Thank you very much for your presentation. That was very good. One thing that in policy is important is to distinguish between what it is Saharan dust and agricultural dust. Do you distinguish land surface in any way, or is it simply the same parameterization for all types of?
This is the same parameterization, and it's information that we have difficulties to take into account, but we clearly take into account this kind of information, let's say implicitly, in how we retune our dust emissions depending on the regions. So there are some dust emissions that are clearly coming from agricultural regions, such as in the Sahel in wintertime. So if you want, this is implicitly taken into account over some regions, but probably not all.
Sorry, there was one more question. Thank you.
Yeah, thank you very much. It was indeed impressive how many things did you tune there. So one simple question. So you look for non-sphericity. Do you consider elongated dust or flattened dust?
Well, this is of a one dimension only, so elongated, I suppose.
So it's like longer.
Yeah, exactly. Only one dimension. Okay. So it's aspect ratio of 1.4.
Yeah. And second question is a little bit more complex. There were 2 times this table appeared overall scores between E-suite and O-suite, and there is overall improvement, and it's impressive, but one thing is really strikingly sticks out of there, this AOD over Sahara.
Oh, that was the Youngstrom exponent, I think.
Say it again?
I think it was the Youngstrom exponent. The red?
Yeah.
I think it was the Youngstrom exponent in the scorecard.
Ah, okay, yeah, thanks.
Yeah. And yeah, it is striking indeed. And well, we'll try to do better in cycle 49.1. I mean, it's also because we have much more dust than before in cycle 48.1 that the much lower Angstrom exponent of dust is having a larger impact than before, and not always positive for that.
Thanks again, Sam. Thank you. Our next speaker is Marianne Schorter-Homstad from DLR, who will be talking to us about the solar radiation. Thank you, Marianne.
Yeah, welcome to the update on the solar radiation team. And I always use this first slide, don't I? Well, that's me. Okay, so you know who's speaking. Well, what I would actually like to emphasize for those who are happy, first assembly here, that we are coupling the meteorological satellite information for the clouds with information on aerosols and water vapor and ozone from the model, from CAMS model, to couple that into radiative transfer, fast parameterization to get time series of radiation. And what is actually new is in the publication list that we now have also a paper out on describing the most recent update. I give you a list of the content of this update in a second. Let me emphasize once again that we have an on-the-fly processing of time series. So if you go to the website, you ask for a location, you get it processed with the most recent version, and can choose different resolutions and so on. What is important for me to say, of course, we are fully integrated in the meanwhile in the ADS, so in the CAMS web page, you find all the documentation there. So we did all this integration. Well, we still find for our users it's extremely important to find the same information on their portals. In our case, for example, the Solar Data Radiation Service SODA. Which is actually also in the background hosting part of the activities. And what is also new here is a logo which is called PVLib, Photovoltaics Library. That's a very well-known library originating from the US, from Sandia Labs, a very well-known renewable energy and other technology lab, MATLAB, Python, and so on, all available. And it's fully integrated there, so users using actually PVLib, and they don't really realize. It's what I called CAMS Inside some years ago. Yeah, that's now here really done. It's a routine called just get CAMS. And yeah, we are also providing a pre-calculated gridded data set. We are ready very soon to update that to an 0.1 degree gridded data set, extend out to 23. So you can download, if you have the need for many locations, you can download this one. Okay, this is a table of what we actually introduced in the last 2 version updates, 4.4 and 4.5. And you see one group in the version 4, which is mainly updating, first of all, the calibration of our satellites. We had a bit to correct what HumanSat is doing. And then we updated many things in the cloud retrieval scheme. Now, in version 4.5, we went to the CAMS reanalysis, replacing continuous evolution over MAC reanalysis, several CAMS near real-time data sets, and now we are really using only the CAMS reanalysis until 2022, and then, of course, the near real-time service. And overall, we are not forced to do any bias correction anymore, which is a good news for us. I really, really love it. And that's the value of being on this track with the most recent aerosol developers as you are here. So this storyline turned out we had at the very beginning telling to European Commission. This is just an example of 1 minute resolved data. Normally we don't show that to users as we are comparing 1 centimeter square observations versus a bigger satellite pixel by that. But you see here in the different versions in the middle row, you see, for example, the diffuse radiation. And you see in the old version, there was a capping on the top values. This is now gone. It looks much more physical. The direct radiation on the bottom. It really looks like you want to have a scatter plot looking like some strange features are simply gone now. So this is a, let's say, very total overview. So now, Johannes, cycle 48R1 results. We are also comparing always with against clear skies, or cloud-free solar radiation observations. That impact do we see from the NEO cycle? And this is actually global radiation, diffuse and direct. On the right-hand side, all the stations we look at on a worldwide scale. And actually you can use at the reddish and bluish color. That's the positive or negative impact. Blue is good, red is If you could read the numbers as I can do, you see 0 point something on the left. It's red, but it's very small, so it's okay. Very slight degradation, 0.5%, we don't care. That's okay. What we really love is the -9% in bias reduction, the diffuse radiation, and then overall it's about 1.7% with bias in the direct, but the diffuse is really much better. And if we now look into the root mean square errors, you see a lot of more bluish in the colors, and you see always a minus on below. Global, not much impact, but that's to be expected. We are now monitoring changes of the aerosols mainly, and the diffuse again, -6% in root mean square deviations, and -1% now in direct radiation. That's really what we're looking for, and that's really from us also a big plus, and go ahead. 49 is welcome then to come next. Okay. So this is work done to support our quality control work, which we do on a regular quarterly scheme as well. This is a more worldwide accessible database for us from all the networks of input data we can use, all historic data. And really what is important for us is now harmonized data access. Independent what the providers do, it's now CSV and NetCDF in one format as we like it. And you can imagine that's a large, large work behind. And then there's this nice button called Visual QC. And if you press on that, you get a dashboard-like approach. And that has been months and years of discussion in the scientific community of the solar energy people to agree on these quality control standards. And we are trying really to convince the community and well, not just to do what we do, but to have a joint understanding and relearn from the others as well as they do from us. And this is really a contribution to the International Energy Agency activity here, which is very nice and very well seen. Recently, we also participated, besides the quality control of the ground observation data to control our products, we also contributed to a worldwide benchmark of model solar radiation data with 2 versions of the CAMS. And here, 2 participants from the team actually took part heavily. It's a nice report out comparing all the different data services here. You can have a look on very detailed, all the scatter plots are published. That's, I think, very nice made. So then we're preparing actually for our clear sky model to make more profit of all the nice aerosol developments. At the moment, we do a mapping of all what you do to the old opaque world, which of course can do much better now, but we have to make sure that we also can use that. So that's actually a next step to come. So the design is completed, we are testing now, and hope next year we can say it's fully implemented online. What is the main thing? We'll now go for azimuth factors, single scattering albedo, and absorption also exponents as really input to our scheme. So by that we can follow easily all your improvements on the optical properties, which seem to be each half year. Okay. So next big step for us, going more around the globe, extending for Himawari field of view. So we have all the data we processed back to 2016. Online processing trains are running. The last few steps of ADS are ongoing. We will have a silent launch during the summer, and probably after the summer break, a bigger information to users on the main conferences. And one thing we're really digging into, I draw a box here, which has a name. This name is I'm Not a Cloud. But actually, most of you who are in the field of retrievals know that we have what we call the plain parallel assumptions if we deal with clouds in modeling or in retrieval. And obviously, I'm not a cloud. Real clouds look like that, what we all know. That's the sky camera network we're operating. It's satellite images, it's from below. Obviously, we are far from having this box-like homogeneous approach. But how to evaluate that better? I mean, at the end, I don't know what is over Valencia today more than what the satellite tells me. So it's a bit a hen and egg problem, isn't it? So what we actually look at now more and more is that we tell us, the radiation observation tell us what the cloud impact is. So this aggregating summary information. So we look at radiation surface radiation measurements, classify them in variability classes, and then start looking at our metrics, like here is bias in global radiation. And you see these classes 5, 6, 7 on the right-hand side. Those are the more variable conditions with thick clouds. There we really see the biases coming up, and that's what we expect to look into. This is kind of a diagnosis tool, but we can monitor our improvement. So we are trying to get beyond in monitoring ourselves. Or this is what the satellite believes in the same situations. It's low, medium, high, or thin ice cloud. That's what the satellite can tell us. It's the best estimate. It's wrong. I'm not a cloud-like style information, but how can we use it? So that's we try then also to use and to monitor. Okay, that's all Cameo, coming to Cameo. Now, coming to radiation forecasts. The CAMS IFS does radiation forecasts, and users really want that. I just received a message from the major, the institution running the energycharts.de, which is the major monitoring of renewable energy production in Germany. They're just asking, can we get the CAMS forecasts included? But can you please go for 7 or 10 days? So I have this written statement for the URD, we just got it yesterday evening. So it really would be nice in 49R1 to say it's 10 days forecast. The users really, really want it. We looked at it. This is worldwide statistics. This is on the first global horizontal radiation day 1, day 2. The reddish one is the non-CAMS, so the high-res standard deterministic model one. You see a biases in RMSE, and we have to say they're doing better than the CAMS with the lower spatial resolution, as we all know, for all sky conditions. Okay, good news for them. There is a statistics on the bottom here, and you see here, this first row is the standard resolution, and the second row is the 5x5 spatial aggregation resolution. And we were used to have that strong decrease in RMSE if we do spatial smoothing. This is nearly gone. That's really good news for those modeling, and we interpret it as a reduction of the double penalty effect. But then if we look into Morocco, so more dust-affected station, now you see the green one, the CAMS, is doing much better as we have the aerosols inside, as we expect, but now we really can show it, improve it, and we do it now in an annual scheme of continuous monitoring of the radiation forecast, as users are very happy to have open data solar radiation forecast provided on a, even worldwide scale. They're ready to test it. Okay, our next steps, well, go for Himavariate, finalize all that, have really a new acronym, CAMS Radiation Service, you know, but CAMS Radiation Service Grid and CAMS Radiation Time, that means really having all the full ADS now, the integration of the gridded data set here, and we'll introduce this new acronym to the users. Version 4 of the Clear Sky scheme, replace mapping of opaque aerosol types. It will be the next story for us. I hope that will include also circumsolar parameterization, which will nicely make use. Go ahead with the forecast evaluation of the CAMS IFS and also the IFS, and of course, MTG. Of course, that's also very soon. So we have to work on that. We don't need to be operational with MTG on the first day. It's going on operational mode because we will have time series, so we need a certain duration of a time series to get it valuable for users. But anyhow, it's on there. We should work on it. And I think the last slide is just giving references, my contact details. So please see me in the break or email or whatever. I'm happy to answer questions if I have time now, but I'm not sure. So, please, thank you very much.
Thanks very much, Marianne. Great to see the improvements in aerosols from 48R1 leading through into solar radiation. And yes, we do have time for questions. Is there any question? Is there a microphone?
There's one on the front.
Where's the one on the ground?
Thanks for the nice talk. So I have a very simple question really in cycle 48R1. We now have stratospheric chemistry. Quentin has showed that it decreases the biases, especially in the tropical lower stratosphere. So I wondered if you were able to see an impact on your solar radiation forecast in the tropics due to that or not?
I'm sorry, I cannot really answer that because we look at it as a whole. We look at broadband irradiances, which somehow hides the ozone influence a bit. Yeah, we would need to look spectrally to really see that. So it's for us not a major, we should not have a constant value, but a meaningful climatology or some value does the job. So we don't really look carefully into that due to that. And yeah, mostly it's what we see is aerosol impact. I'm sorry, but that's because we broadband.
Thanks.
Thanks, Marion. So our next talkers are Claire Grenier and Vincent Huinen, who are going to be talking about missing CO emissions, I think.
Thank you. First, I will start the talk and Vincent will continue. And just to tell you how it works, so we have CAMS 261, which defines emissions, and thanks for all the CAMS 261 group for providing all the different inputs. And we have the other group, CAMS 235, which is testing the emissions and tell the modelers to try to, the people preparing the emissions to improve the emissions if they can, and so on. And then when we are happy with that, we integrate into the global production system. So what we will report here is a discussion we had for the last 6 months or even more about how we can try to improve the modeling of CO. So why we look at that is when you look at the performance of carbon monoxide, you see on the top left tropomi CO, the model bias, and you see that all over the northern hemisphere, and especially mid-latitude, you have a large negative bias. And first in the spring and so on, and in the summer, the bias is still there, a bit less, but it's still there. So can we explain it, and can we do something about it? Yeah, and you see, it's not only it's a problem of satellites, it's not, because when you look at the values from IAGOS here in black, you see that if you look at the model before assimilation, you are still biased low. So the thing, why do we really care about that? Because we could say, okay, let's just assimilate CO. But when we create long-time series, and Ansha will maybe talk about it, maybe not, I don't know, but at least you might have jumps when you change the satellite because they are not exactly the same and so on. So when you introduce, for example, tropomi, you could have jumps. So we would like to have a good CO modeling. So this thing is not new. This bias. This is a paper that was published in 2006, and a few of you here in the room were co-authors of this paper, where you see the same bias. This is tropomi on the top, and on the bottom right, you see a station in the northern mid-latitude, where you see the observation, and you see mostly in winter and spring, you have a negative bias. And there was a paper also, in 2014, and some of you are also co-author of this paper, where you see in red the model as it is. So on the top left, you see really the bias. And there were, in this paper, different tests on multiplying by 2 anthropogenic, biogenic fire emissions. And you see, even with sometimes by multiplying artificially the emissions, you don't correct the bias. So this, I will just go very fast to it because Vincent will come back a bit more on that. But basically, what CO is made of is a third is VOC oxidation, a third is methane oxidation, and a third is direct emissions. And OH is also playing a role. So we'll come back to that. And so what I will show you is the work we did in the CAMS 2 is 61, the emission group. So we developed the new emissions. So there is version 6 now of this CAMS GLOB-ANT, so global anthropogenic emissions. And on the bottom, you see one of the bases that we use, which is EDGAR, and the last version in the dark blue is much smaller. So we said, oh, we will get even less CO. So we said, okay, let's not use it, and because it's way too low. But is it really too low? And these are two studies that were published recently. So the first one on the left is for the US. The blue values are based on real observations, updated emission factor and so on, and you see that compared to official, so NEI, National Emission Inventory, for the US, the emission seems to be smaller. And on the right, it's a paper that was accepted 2 weeks ago or something like that, where we compare different inventories in Colombia and with local observations and measurements, and the blue ones are the local values. The red one, plain line, is the EDGAR 6, so the lowest values, and the other ones are the other inventories, which seem to show that our CO emissions are not overestimated, but are not underestimated, but overestimated. So it's really puzzling, all that. And this is also 2 plots with, and the top one is using this new version, the CAMS Global Emission 6.1 in black, where you see that we are not really lower than any other ones. We are, I mean, average in the same. So, and you see in the, no, Maxit is not there on that one, but, and you see here the Western European emissions, where all inventories really agree with each other. So it's a paper that will be submitted next week or so, and then Vincent will tell you what we did for the modeling.
Yes, so the modeling is saying something differently, unfortunately, and this is the whole issue really that we need to get together there. So where we started off from is, well, it must be the emissions that are wrong, and I did some tests. First of all, with this version 6.1, and but that would give similar biases as what we have now. And then I did 2 other tests where I just scaled up the emissions by a random factor. Well, it's not completely random, but this 30% increase and another one with 60%, because that is what the satellite will tell you, and that is also what inversion. So if we move towards inversion methods where we optimize carbon monoxide by optimizing emissions, you will get it from the satellite retrieval as well. So that's what you would get with inversion studies, and this 30% anthropogenic emissions, that is what I miss. Well, I will come back to that. Don't worry. And the same conclusions hold actually. So you can say, well, the satellite is wrong or so, but also if we look at surface observations or aircraft observations, we see the same pattern that we miss the carbon monoxide in the lower troposphere. But yeah, so. But then we started really the discussion, and Claire just explained, well, there's no reason why the carbon monoxide anthropogenic emissions are biased low. They might even be biased high. So that was really so it's very good that we have these meetings now on a regular basis, and that Claire challenges me and I challenge her to look at our things that we are one system in the end, and we need to have this interaction, and we look at again at the plots, and then I look at the chemistry budget, and we can go through this whole list of aspects that also could contribute to the biases. So there's the anthropogenic emissions, which is it's on one hand rather obvious if you look at China or so, or Europe, and during winter time there's no chemically active process that can explain these low bias here. So that's still one important thing that could still explain uncertainties. But there's others. There's more to it. There's also the issue of the lifetime, which explains quite a bit how long CO resides in the atmosphere. And then there's looking closer and closer. We also noticed that the dry deposition is actually quite high compared to what we used to have before. And then there's issues with biomass burning emissions, biogenic emissions, VOC. So there's a whole box of Pandora that's opening up. And I'm afraid that we didn't solve the carbon monoxide issue. And that's where I'm fortunately end with our conclusion. So the good thing is really that we have this interaction going, and I'm very pleased with this to challenge us, and we challenge the emissions group. So this increase that I showed, it's not reasonable, probably. So that's what Claire points out. We could do more sensitivity experiments. We have done more experiments already with the dry deposition. There can be more that can follow to look closer. But until this is solved, I still would like to make the case to artificially increase the carbon monoxide emissions, just for the sake of consistency. That's my point of view. But any other ideas are, of course, very welcome. So that's all. Thank you.
Thank you both very much, and I very much look forward to seeing the results from this discussion. We do have time for questions, if anyone's got one. No, if not, moving on, Angie and this will give the last talk of this morning, looking at the Cameo project. Thank you.
Yeah, thanks a lot, Mel. So I will give an update on the CAMS evolution project Cameo. Cameo is a Horizon Europe project that aims to support developments with focus on aerosols and reactive gases for CAMS. It's a 3-year project, 7.5 million euros with 22 partners in the consortium. And it aims to do TS3 research, so longer-term research than we can do in the CAMS core service, and perhaps also slightly riskier aspects that we wouldn't tackle with the normal CAMS core service. We have 22 partners, as I said, from 12 European countries, and you can see a map there. So Cameo consists of 7 work packages. We have 3 work packages there on the left that deal with new data and data assimilation methods. And then we have 3 work packages that deal with providing uncertainty information for CAMS products, and 1 work package on project management that keeps us all on track. A lot of the Cameo partners are also partners in CAMS, so there is a very close collaboration between CAMS and Cameo. And a lot of the Cameo results will then feed directly into CAMS and benefit the CAMS users. We also have a few new partners in Cameo, so we bring in new expertise in addition to what we already have in the CAMS consortium or CAMS group. So the first work package deals with the assimilation of aerosol in the global IFS model. And here, it's important to know what we currently do in CAMS is we assimilate retrievals of aerosol optical depths, for example, from MODIS and VIIRS. But it might be beneficial to assimilate aerosol visible radiances directly, because then we could have better consistency with, for example, clouds or surface types of the IFS. So Cameo will carry out a proof of concept study to build the infrastructure for such an aerosol visible radiance assimilation scheme, and then carry out tests with this scheme and compare it with what we currently do in CAMS. And the next task deals with retrievals of aerosol optical depth and also other parameters, preparing CAMS for upcoming new satellites such as 3MI, MAP, CO2M, and also the various Sentinels. And here we will try to harmonize aerosol retrievals, because there's a lot of assumptions going into the aerosol retrievals, but they can vary depending on which instrument you are looking at. And if you think of producing a reanalysis data set where we have several instruments coming and going over the overall period, we can get a lot of changes just because the retrieval algorithms differ. So we try to harmonize this as much as possible using the GRASP system, and also using CAMS aerosol parameters in the retrievals and bringing it in line as much as we can with the model. And we will then produce test proxy data for 3MI simulated data with a conventional algorithm, and also with the optimized retrieval adapted to CAMS needs, and compare the results. The last task for the aerosols deals with the development of new observation operators to, for example, assimilate aerosol angstrom information. At the moment, we only use AOD. And here, it's very difficult normally for external partners to work directly with the IFS data assimilation code. To make this easier, the first step here is to build an offline observation operator. So take the IFS code, have an offline version, and once that is in place, this can then be extended for new species or parameters, and then be built back into the IFS to allow CAMS to assimilate these new species. And currently, an offline dust aerosol operator is being prepared. The second work package deals with the assimilation of reactive gases in the global model. And here, again, the first task is to prepare for new satellite data. And here's a big focus on the upcoming geostationary air quality instruments. So we have Sentinel-4, the European one, and then also GEMS over South Korea, and TEMPO, the North American one. And because Sentinel-4 isn't flying yet, we will use GEMS and TEMPO data to prepare the CAMS system for the use of these data. And for example, at the moment, we are acquiring routinely GEMS, NO2, and ozone data from Korea, and we're starting to monitor them. And you can see some first plots there at the bottom left. These new data sets, and also some of the ones we currently use, like Tropomi, are a lot of data. So for example, Tropomi, you're looking at resolutions of 3.5 times 5.5 kilometers compared to our model grid boxes of 40 by 40 kilometers. So we really have to average the data or thin them. And to do that in a clever way, we use super obbing. So we average the data, do something clever with the observation operators as well, observation errors as well, and then use products that are more representative of the model resolution. And Cameo will take a super observation software developed by KNMI and implement that in the IFS. Another step will be to implement a system, an inversion system for biogenic emissions. CAMS already has the IFS emission inversion prototype that's being built under the COCO2 project for anthropogenic emissions, and we will extend this to biogenic emissions. And for this, in the first step, we're assessing the quality of the data we want to use. So we are looking at Tropomi data here, we're developing bias corrections for the data, and we are also, here, the second plot from the left, comparing the model data with independent data, so here with aircraft campaign, to get a feeling for the quality of the model. And then the final step of this work package is to improve the data assimilation methodology and go to a weak constraint 4D VAR for some of the stratospheric long-lived species. So at the moment we use what's called a strong constraint 4D VAR, where we assume that the model is perfect, but the model does have errors, and in a weak constraint we model these errors explicitly. And work has started. The code is in place to do this for ozone and water vapor already. We still need the error matrix for the model error that is being produced at the moment. And we're also assessing the quality of the data and assessing whether the observation errors and the background errors we are currently using are okay. So yeah, this is all coming along nicely. And then the next task looks at the regional ensemble to improve the data assimilation in all the regional models. And these models currently mainly use surface observations in the assimilation, and the first task will be to improve or implement the assimilation of species from Tropomi in all the regional models. And then the next task will look at improving the data assimilation of aerosols. And here we will look at ground-based and spaceborne data. And one example here at the bottom, the plots show the benefit of assimilating surface and satellite data for NO2. You can see the top left is the S5P NO2. The top right is the model. You can see the model has a low bias. If S5P is assimilated, you get the bottom left where the columns look very good. If the surface data are assimilated, you get the bottom, sorry, the other one was the bottom middle, you get the bottom left if only the surface data are assimilated, and you see there's mismatches. But if you assimilate both, the surface data look good and also the columns. So there's definitely benefit from that. And then the last task is to prepare the regional models for the upcoming data. And here, obviously, they can't use GEMS or tempo data because they are running over Europe. So they will carry out observation system simulation experiments, or OSSIs, to produce test data and then assimilate these test data to be ready for when Sentinel-4 data come. The Work Package 4 will look at providing uncertainty information for CAMS solar radiation and deposition products. And it's very nice talking after Marion because she's introduced the solar radiation service very nicely. So the first task will be trying to exploit new additional solar radiation data for validation and assess the value of having additional data, and also look at why do data from various stations differ. Task 2 will look at acquiring and exploiting deposition data, because CAMS has deposition products, but we don't really know too much about how the quality of the data is. We also perhaps need some more user feedback. What do the users really want? So we need discussions with stakeholders on this. So it'll be data acquisition and then also making sure we fulfill the user needs. And then the last task here will be to develop methodologies to derive uncertainties for the radiation and deposition products. And for the radiation products, they'll use machine learning algorithms to come up with uncertainty estimates for all the radiation data points. And we will run an ensemble, an NWP ensemble with atmospheric composition information that will then allow us to come up with deposition uncertainties. Right, the next work package is about emissions and surface fluxes of CAMS products, both for the global and for the regional models, and deriving uncertainty information here. So we heard in Mark's talk yesterday that there are differences between different emission data sets, but we don't really know what the uncertainty of the individual data sets are. So the first task will look at the uncertainty in the emission temporal profiles, so how the emissions are spread, say, over a day or over a week or the months over the year, and come up with a spread of that. The next task will look at uncertainty information in the global isoprene emissions, and this will then feed directly into Work Package 2, where we can use this information in the data assimilation system. And here we will run the Megan model with various scenarios, varying input parameters to see how that feeds through into the final product. And we will also provide uncertainty information for the regional and global anthropogenic emissions. And then in a final task, evaluate the quality of the CAMS global NO2 and GHG inversion products by comparing with other data sets, and also with the DEXO KNMI system to look at the NO2 inversion. And then the final scientific work package looks at CAMS policy products and global forecasts. So we have a lot of we have reports and also tools to understand the origin of pollution episodes, or to play, for example, with the CAMS air control toolbox to modify emissions and come up with your own emission reduction scenario. And we will provide the 3 tasks that will provide uncertainties for the policy products, one related to nonlinear chemistry, one related to the local scale. So how does the what is the uncertainty compared to local pollution and long-range transport, and how does it depend on the model resolution or the definition of the city? And then there's also some studies comparing with other studies to come up with more uncertainties for the sector and source contributions. And work has started here as well, running regional CTMs with exactly the same configuration to establish how important is the chemical uncertainty compared to the methodology used. And the last task of this work package looks in the uncertainty of the global CAMS forecasts, because that's often a question users ask as well. So we will try to quantify several aspects. One, by running a 51-member ECMWF NWP ensemble with atmospheric composition information to provide meteorological uncertainties. Then use the emission uncertainties provided by work package 5 to see how that feeds through into the forecast. And then also use the deposition uncertainties in collaboration with work package 4. And I think that was blocked out here in this format. We also look at the uncertainties depending on various chemical schemes. The 7th work package is the project management, and here I just want to advertise we have an external project website now. I think it's still a bit work in progress, but the link is there if anybody wants to look at it. And then the main impact of Cameo will be through CAMS, because we work so closely with the CAMS system, and all the improvements will feed into CAMS and then benefit the users. And in addition, there's also impact on, for example, satellite retrievals from the work done in work package 1 that can then benefit future satellite instrument designs, for example. So I just leave you with a slide showing the whole consortium. So this, it's a big group and it's very exciting work. So thank you very much.
Thank you, Angie, for such an interesting talk. So much interesting work going on, and I look forward to seeing the results. I suggest we're at coffee time, so if you do have a question, perhaps speak to Angie directly. Thanks again to all the speakers this morning, and I hope you all enjoy coffee.
Okay, I think most people are in. There's still some people coming in, but we should probably make a start so we can be finished for lunch and have a full hour for lunch. So this is now the session, the last sort of fully scientific session of the GA. It's going to be on greenhouse gases, and we're going to start with a perspective from DG Klima on CAMS and greenhouse gas monitoring from Tom van Ierland from DG Klima. So Tom, over to you. If he's yes.
Hi, good morning. Just to check, do you hear me?
Yep.
Perfect. Yes, Tom van Ierland. I work for DG Klima. Maybe to frame very shortly what I do, I work in a unit that is actually responsible for a number of topics. Among them are the role of digitalization and the role of Earth observation in climate policy. As such, I support, or the unit with whom I work, supports several other units in DG Klima doing policy development and policy implementation. That's what I would like to talk about today. I'm going to bring three examples of where satellite data starts to penetrate how we prepare or do policy. And I will wrap up with a few other examples without going in further detail. As such, I don't think I'm going to do a scientific presentation. I just would like to underline why your community and your work is of increasing importance for us as policymakers. The first use case I wanted to touch upon is inventories. And then we're talking about inventories at large of anthropogenic greenhouse gas emissions. That can cover all fluxes, but of course CO2 is the most important one. That can come from all sectors, be it the energy sector, be it the land use sector. Typically, we as policymakers are confronted with inventory systems that work on activity-based data. I don't think we are displeased by that. I think we have over the years learned more and more what are the strengths and weaknesses of inventories. But we would certainly also would like to have more tools to double check our inventories to see if the direction that we see of emission profiles in inventories is the correct one, to see if there are large differences between, for instance, emissions coming from certain areas, yes or no. The primary tool to help us there is inverse modeling, but inverse modeling needs data, and that data can come from satellites, that can come from airplane monitoring, or that can come from in situ data. We have seen important developments there. I know that our colleagues of DG DEFIS, together with many in the room there, are working, for instance, on the Copernicus CO2M monitoring mission. For us, that are clearly tools that we need and that we think are useful in the future to support, or at least to inform, if the inventories we are having, are in the right direction. Another example for us there is the work by GRC in the EDGAR database. The database itself is primarily based on activity data, but more and more they are linking that to inverse modeling to double check if the inventories are going in the right direction. Then another type of policy tool, and that is not the inventory, at a large area scale for a full year, but rather the instant type of emissions. Where is there a point source emitting today that might be avoided? There are different types of point sources that could be of interest. Think about forest fires, for certain. But one where we presently see a lot of policy development is methane emissions, and then notably methane emissions from the oil and gas sector. There, the use of satellite data is really, you could say, the primary resource to be able to intervene fast and on a very large scale, being at a global scale. We saw with the leaks in the Baltic Sea from the explosion on the gas pipelines that satellites can pick up fast that something occurred. In that case, it was much more difficult to use a satellite to estimate the quantities. But it's a good example of what the tool can do. We as policymakers are interested And actually, my colleagues in DG ENER are actively working with, for instance, IMEO from UNEP to see how their tools can be used for a policy setting. Also, again, we understand that the CO2M monitoring mission will be able to look at methane data. What is interesting, actually, that once you have a tool that functions, that gives you regular, very frequent, if possible, data on a global scale, you do get questions around governance. And that's not something that we have to go into today in much detail, but basically the question is, if you see a leak, who picks up the phone and who do you phone? That requires a governance part, and that is certainly something I also think in the coming years will need to be developed. In that context, for instance, you have in the EU right now a legislative proposal on improved monitoring and avoidance of leaks in the oil and gas sector being negotiated with our co-legislators. And in there is actually the requirement for us as Commission, and in that case DG ENER, to set up such a monitoring service. A final example I want to give is land use. So now I'm not thinking about a point source emission as such, being forest fires, for instance, but rather how does your land use change over time? And what does that mean for the amount of emissions or removals the land use sector has contributed to the global atmosphere? Again, there, satellite data is very useful, again, because you could do it potentially at a global scale in a uniform manner. The legislative part there from the side of the EU, and I think that is a quite interesting development. We have very recently agreed on a new land use change and forestry regulation. And that regulation for the first time requires member states to use geographical information systems to provide information for certain land areas, notably the ones which are carbon rich or biodiverse. That could be satellites, that could be aerial monitoring, but clearly it is a new development where member states will start to have to include that when on an annual basis they provide information to us about what happened in their land use sector. So these are just 3 examples where for us satellites are starting to impact the way we do policies. I wanted to briefly just say that it doesn't stop there, but I was asked to talk very short and I think I'm already over my 5 minutes, so I apologize. But just a few other examples, and I think they probably are all familiar. Simply the science of climate change, how atmospheric composition changes and impacts climate change. Think about interactions of the gases regulated typically under Paris, but also how it impacts other types of emissions. Think about very short-lived climate forces, aerosols, and even still ozone-depleting substances and how they interact with other greenhouse gases. The whole area of climate impacts, resilience and adaptation, where also satellite data is certainly of interest. And then again, 2 examples of very specific, what we call MRV applications, monitoring, reporting and verification. One of them is to see if satellite data could be used to double check if inventories provided by ships, and that I mean seafaring ships, is correct, because you can link the activity data of a satellite of where a ship goes to what the ship potentially has reported as its emissions under our monitoring legislation. And similarly, but I think that is still science in development, linking satellite data of airplane movements together with meteorological data on what that means for contrails and the associated non-CO2 climate impacts of airplanes. So again, a very fast overview of all types of policy fields where we have an interest. And I have to say, if life would be calmer, but it isn't, sadly, I would love to be present in these types of conferences. But as I said, the policy files are quite busy in Brussels, so I apologize that we couldn't attend this session. Thank you very much.
Okay, thank you very much, Tom. I think we need to move on. So as Vincent said the other day, if any questions, you can send them to us and they'll be answered offline. The next talk is an update on CO2 MVS from Richard Englund.
Good morning, everyone, and thank you, Tom, for this nice introduction, setting out clear user requirements for what we're trying to do within this whole new development as part of CAMS. So very good to start from the user perspective and now trying to see, well, how are we going to tackle the problem? I'll give a brief introduction. There will be a lot more in the following presentations for you to enjoy. So I'll try to be concise. This is again the figure showing CAMS in its second configuration after phase 1. What are we going to do in phase 2? And Vincent, I think yesterday already pointed out the different elements. We have already discussed the national uptake scheme, the national collaboration program, the Copernicus thematic hub. But then there's also clear new developments in terms of emissions. Greenhouse gases, but also for air quality where it makes sense. The challenge we have is that we can't observe emissions directly. We observe the impact of the emissions, the result of the emissions. So we need to be clever, we need to bring things together to make sure we can use Earth observation to provide added value information that's useful for the policy sector, for the scientific community and many other user groups. So the whole idea behind this new development is basically do what we do well, what we have been doing within CAMS, what we have been doing in numerical weather prediction for many decades, is bring together information. We have observations, we have prior knowledge, for instance, the inventories or activity data. We can model to some extent elements of the carbon cycle, integrate that in a data simulation system or inverse modeling system, whatever you want to name it. And in this case, we focus on global and local scales. Do evaluation and quality control, a very important aspect of what needs to be done, and provide the outputs. Generate enormous amounts of data, but we can't stop there. There's a pink block there as well, which is critical. How do we make sure this data is useful for the different user communities? So we need to be developing new ways based on the experience we already have within CAMS, within C3S, within the other services, translating the enormous amounts of data in policy relevant information. So that's the whole idea to be implemented within CAMS, but of course together with the other Copernicus services and with the space agencies, ESA and EUMETSAT. We didn't start yesterday, we started actually quite some time ago already, and we've talked about this in previous CAMS General Assemblies already. The whole thinking started in 2015, where there was a panel of experts thinking, well, what do we need to do? How do we form this? And since then, we've evolved through a whole series of research projects, and I'll come back to that in a moment. Also, satellite missions being built and launched. Sentinel-5P, we've seen examples already, is in orbit. Sentinel-4, Sentinel-5, and CO2M still to come. But we're getting closer and closer to where we need to be. We want to be operational in 2026, which is linked to the second global stocktake, which is starting then from 26 to 28. Also, the launch of CO2M is linked to this. Quarter 1, 26 is the current estimate. So we need to work hard to make sure we are ready for this. There's not a lot of time left. There's a lot of work that has been done, but now we are in a phase where we need to start implementing things. Again, we work on global and local scales. This has been what we've been asked from the Commission, supported by the experts. Focus on individual point sources, as Tom already pointed out. For instance, for methane, this is a very clear example where you can have a very quick impact in terms of mitigation. But then also monitor on a global scale. Follow the carbon cycle, follow the emissions, as well as the natural changes, some of them caused by climate change, on a global scale. And we want to make sure we are consistent between the two, try to link things. There's an obvious one, going from global to local through boundary conditions, but we also want to try to see how we can use the local estimates to further constrain the global system. So this is all work in progress. I won't go into detail here, but it sort of sets the landscape. talking about these research projects that I just mentioned, we have been really lucky that the Commission decided to set funding aside to really give this development a great push. I've listed here the main ones. There's actually more than these if you really look at greenhouse gases. So in Horizon 2020, we've had several projects. Some of them are still running. In Horizon Europe, we have new projects. And you will hear from some of them in later talks to show what has been done in these projects. COCO 2 has been the main one in terms of developing the CO2 MVS, developing the prototype systems, but we've had great support from other projects like Verify, like ICOS Cities, and now in Horizon Europe with these new projects as well. We're not starting from scratch. We actually have been providing greenhouse gas products within CAMS for quite some time. You will hear a little bit more about it also in the next presentations. But just sketching very quickly, 3 atmosphere data store. There's already information about the inventory-based emissions that have been discussed already in the past days. We have annual updated flux inversions using satellite data and in situ data to constrain fluxes of CO2, methane, and N2O. And we have daily global forecast and analyses of CO2 and methane already. So this is already there. We just want to build on top of this and then make it much more extensive. Some milestones over the past year, just a few things I want to highlight. We've been working hard through these projects, but we are also already interacting with different user communities and also with the international coordination efforts. A nice example has been that Germany has already been using CAMS results in their reporting to UNFCCC. It's still in a sort of an experimental phase, trying to see what this information can add to their required reporting, but it's the first step. It's really talking to them, working together to make sure that this evolves. Another example is from the COCO 2 project, where we put together the most mature developments we've had within the project and made a submission to the first global stocktake. So we have some use cases, some examples of where we are, what we can do, and submitted that as part of this discussion in the global stocktake. We've been present and showing results at COP 27 in Egypt last year, showcasing again where we are, what we aim to do. So very important in terms of communication. And then we also try to collaborate as much as possible internationally. C2 MVS, it's a long acronym. The S stands for support. This is really important. We are there to support the Commission, to support EU member states, but also to support the international community. So for us, therefore, the WMO framework, the Global Greenhouse Gas Watch, is really important to help develop these new services. And a few other things that we have been doing in the past year. Tom van Ierland already mentioned EMEO, and we have had discussions with them. How can we work together? How can we, as CAMS, contribute to the efforts they do under the UN coordination? We've had significant progress in COCO 2. You will hear more about this later. Start of the Corso project, and again, this will come later. A submission of a new proposal, Katrine, which we hopefully will be funded. We don't know yet, but to improve tracer transport, for instance. And then working together with the other projects that have just started as well, and especially in terms of the user interaction. We try to coordinate our efforts within the different projects to have one common voice to the user communities. That's all I want to say as an introduction. Again, we'll hear more about these different aspects, about what we already do within CAMS operationally, what is being developed within the different projects, how we look at quality control. All these things will be coming up in the next few presentations. Thank you very much.
Okay, thank you, Richard. So again, in the interest of time, I think we move on to the next one. And the next one is Frederic Chevalier from CEI talking about updates on GHG developments in CAMS.
Thank you very much, Mark. So I have the difficult task to present the developments of 3 services of CAMS, 52A, 52B, and 55. It's all about greenhouse gases, and actually we are striving in the same direction, so it's just a matter of putting the jigsaw pieces together. Within CAMS for greenhouse gases, we have two types of products. On the left, we have the high-resolution near real-time data that are provided. This is around the IFS. The map that is shown here corresponds to the methane forecast for now, basically, that was issued yesterday. So time is critical here. To do that, we need to have satellite data that are accurate and also provided in near real time. And it's a service which is not done currently by the space agencies because it's very expensive. So we have to do it ourselves. So that's one part of the service. Now, at the bottom, we also need to make this service run. We also need to have good estimates, prior estimates of the CO2 and methane fluxes, absorptions, and emissions. So this is part of the IFS, but we do support this by helping the developments. And on the right, this is the other type of product that we do provide within CAMS for greenhouse gases. It's the low latency. So after a few months, we do large reanalysis with long windows. So it's a very extensive work, computationally speaking, and it's done at coarse resolution. So high resolution, fast, or low resolution, more accurate, but slow, basically. To care for these three parts, so up, down, and then on the right, we have 8 partners in 5 countries. You can see the names here. In the room, we have Ario from TNO, Philippe Pellin, a bit, I don't remember exactly in the room, and myself. We do, within these 3 components of CAMS, we do invest a lot in the service evolution. And this is, well, of course, quite common within CAMS because the evolution is quite fast. But for us, it's particularly important because, as Richard mentioned, in the horizon, we see the CO2 MVS coming, and we really want to be part of it. We want to provide building blocks for the CO2 MVS, at least for the integration and modeling part. So within this last 12 months, there has been a lot of activities for the development of the service, either to maintain the input data flow, make sure that they are still alive, basically, or to develop the service towards more accurate products. So I have one slide, basically, for each one of these items. And then at the bottom, I just wish to mention that we are taking the best of the current paradigms in terms of computing. I will talk about artificial intelligence at some point, and also about graphics processing units, GPUs. So the first point is about maintaining the input data flow. We currently use a lot the GOSAT satellite. It's a Japanese satellite that provides critical information to the system about CO2 and methane. GOSAT was launched in 2009, and so any day, basically, this 14-year-old instrument could die, even though currently it's still in good health. The Japanese launched GOSAT 2 a few years ago. That was in 2018. And so there is no urgency, but just to make sure that we have all we need on the day when GOSAT dies, we adapted, this is the work here for the University of Bremen, we adapted the chain of the retrieval for the column of CO2 from GOSAT 1 to GOSAT 2. So that was done successfully during these last 12 months, but there are differences. I mean, GOSAT 2 is not GOSAT 1. First, as of now, we do not receive all the spectrum in near real time, or not all of them, and some of the orbits, they come quite late. So that's not a good thing for us. The other thing is that we don't retrieve the column of CO2 exactly in the same places of the Earth. We typically have more data over the ocean, and we have less over land. I mean, after the quality control of what we can do with the retrieval. All in all, we have 10 to 20% less GOSAT 2 data per month than with GOSAT 1. In terms of quality, we have a different statistics here by surface station. So we compare to TCON, the ground reference, and basically we have the same. So in orange, you can see the GOSAT 1 product compared to TCON, and in blue, the GOSAT 2 product. You have different statistical criterions, and it's basically the same. So good performance, different spatial coverage, less data, and anyway, the processing chain is now running in near real time in parallel to the GOSAT-1 chain. Then we have the same transition from GOSAT to GOSAT-2, but this time for the methane retrievals. That's the work of SRON. And it's a bit like the same for CO2. We have now a near real-time processing chain that runs in parallel to the GOSAT-1 processing chain. And we see that the quality of the data that we retrieve from GOSAT-2 is roughly the same. However, this time, given the fact that we are interested in different parts of the spectrum, we have many more data, in particular in the tropics with GOSAT-2 compared to GOSAT-1. So GOSAT is not currently, GOSAT is still healthy, so transitioning to GOSAT-2 is not an emergency. That's different from METOP-B, because from METOP, we use two instruments, YASI and AMSU, to retrieve the mid-tropospheric columns of CO2 and CH4. That's the work of FX Conseil together with LMD in France. And over the last months, we saw a strong degradation of one of the channels that we use to retrieve the temperature information that is needed to extract the CO2 and CH4 mid-tropospheric column information. So you can see here the increase in the noise on the top left, the increase in the noise of that channel. So with this noise, with this channel very noisy now, on the right, top right, you can see the type of map that we retrieve after a month's worth of processing. We have something that shows a contrast between the land and the ocean and a large scatter even over the ocean. This is not realistic. LMD and FX Conseil have adapted their processing chain to METOP-B, and now you get the map on the bottom right, which seems healthy again. There is another strategy which is continuing with METOP-B, but this time changing from channel 6 to channel 7 of AMSU. However, since last December, that channel has also been unstable. So the current solution is really to transition to METOP-C. In addition to GOSAT, we would like to have near real-time data from OCO2, so that's an American satellite, and currently NASA doesn't provide the near real-time service, so we try to do that with neural networks or artificial intelligence. We have demonstrated the capability, the force of the method using, well, in reanalysis mode, so you just reanalyze the full period. However, we encounter difficulties when we are in near real-time mode because we are out of the training dataset. So this is something that we try to address using different methods, different changes in the neural networks. However, it didn't work, I have to say. We are currently re-evaluating the composition of the training dataset, and hopefully a year from now, I will show you better results. So that was for the satellite part. Then we go to the surface flux part, so the provision of prior surface fluxes for the forecasting and analysis system. There was an important work in the implementation of a model of solar-induced fluorescence in CTSL, which is the surface model of the IFS. The advantage of this model is that it allows to assimilate retrieval of SIF, solar-induced fluorescence, for instance, from the TROPOMI satellite. And we are testing this together with the assimilation of gross primary production data for the vegetation, GPP data that are measured at FluxNet sites. So we are trying to improve the model by tuning parameters based on the assimilation of this satellite data and these surface measurements, key parameters that control the GPP and the phenology. The system works, so with just these key parameters, we are able to fit the observations better, so that's by construction, but it just shows that it's a healthy situation. But on top of that, we see that there is a large improvement of the CTSL GPP simulated by CTSL versus independent data of GPP for all planned functional times. So there are ongoing developments, of course, but that's already a good progress. I'm sorry for the presentation, but it doesn't look like that's on my computer. Similar work has been done on the wetland model for methane emissions. So to simulate methane emissions, you need to have a good idea of the inundation areas. So where do we have wetlands and how much does it emit? So there are a number of products that have been tested to get the information about the surface, the area of the inundated areas. So there was a choice that has been made, and there has been a recalibration of the statistical models that simulate the methane emissions. Currently, we have promising results with the IFS test. Again, a very surprising presentation, but it's not my fault. There are other developments of the models that are ongoing, and again, hopefully next year, much more to present. Well, this is a bit embarrassing, because this is definitely not my presentation. So that's for the atmospheric inversion. So I will speak with the hands. This is the porting of the simulation of the CO2 and N2O on graphics processing unit. So we had to restructure the code that was done over the last few months. And now we are able to simulate carbon dioxide and N2O at a resolution which is close to 1 degree. So on the left, you should have seen a map of what we were doing a year ago with 6,000 grid boxes in the horizontal and 40 in the vertical. Now we have 20 more 3D grid boxes over the globe. And all what is left on the slide, apart from the map, is this ghost from Pac-Man. And basically the idea is that we leave the 80s Pac-Man to have something that looks much more modern and with patterns that are much more realistic. Well, the patterns are not more realistic, but at least we have lost the pixelized vision of the carbon dioxide and N2O fields. The story is the same for methane, but the code has not been fully finalized to reach this 1 degree resolution. There are a number of updates in TM5 for DIVA, so the inversion system that are being made, but the situations look healthy, and we should be able to finish by the end of this year with an estimated production time reduced to something like 2 months for this type of resolution, which is quite amazing. An important advancement over the last few months has been the production of a fast-track product. So that's the V22R1 that allowed us to have a first look at the methane emissions over 2022, while with the previous production chains, we would have had to wait until the end of this year. And the advantage is that we were on time to deliver information for the European State of the Climate. With this, I'm done. I think I have tried to show you that we are trying to take the best of the current satellite data that are up there, even though they are not ideal and we are expecting a lot from CO2M. But already with the existing ones, we can do a lot. And we are also trying to take the best of the current computing paradigms so that we can have products that are delivered as fast as possible. Thank you.
Great. So thank you, Federica. Nice job of condensing this information to a little over 11 minutes. Again, in the interest of time, we'll move on. The next talk is on how the CAMS GHG products perform by Isabelle Pisson from Université de Versailles-Saint-Quentin.
So I'm going to present you what we do about greenhouse gases, well, CO2 and CH4 only, validation inside of CAMS 82. And this is actually Michel Ramonet's presentation. So we validate the simulation against various type of data. So you've got on the left the map of all over the world, on the right a zoom over Europe. So we've got remote sensing data with the TCON and NDAC networks, and also in situ data at the surface with surface sites among which ICOS stations, and also the vertical in situ data with the IAGOS flights and the air core, the air cores. So what we do is we try to validate the CAMS near real-time global atmospheric composition of CO2 and methane. So here we begin with the ICOS stations. So on the left you've got CO2, on the right methane. You've got the stations, the ICOS sites from the north to the south. And on the x-axis you've got the date since the beginning of 2022. And the colors are the model minus observation. So it's in ppm for CO2, in ppbs for methane. It's on a weekly resolution with a vertical black line. It's a change in the experiments. So for CO2, there is an overestimation of the seasonal cycle at high latitudes, about 1%, with too low concentration in autumn, too high in spring, summer. And in the low latitudes and in the southern hemisphere, it's a systematic overestimation of CO2 concentrations. For methane, it's not the same issues. If you look at the biases, so 0 is the light colors, and very red is very positive, very blue is very negative. The biases are more positive, larger in Scandinavia, which may indicate an issue with wetland emissions. And we've got, through a gradient, concentrations which are too low in the south of Europe and in the southern hemisphere, when we've got one station, which is La Réunion. And above this, you've got particular pollutant events. So particularly in 22, it was in October, November, which seems to be overestimated. You can see an outlier. So the fourth station from the south, it's actually Ispra in Italy, and it seems to be an outlier, probably because there is an issue with its representativity. So if we look at a particular station, so here we've got Hohenpeißenberg, it's a tall tower in Germany. So on the left you've got still CO2, on the right methane. So it's a level at more than 100 meters above the ground level. You've got the analysis in green, forecast in orange, observation in black, and so it's a time series. So this time it's still mixing ratio, still not the same units for CO2 and methane. So you've got the time series at the top. On the middle panel, you've got the difference between the observation and either the analysis of or the forecast. And on the bottom, you've got linear regressions. So there are no significant differences between the high-resolution forecast and the analysis. At the synoptic scale, the events are well-timed. But when you've got large synoptic events, the methane concentrations are sometimes overestimated. So this is the case in December 22. So this is only Hohenpeißenberg, but it was observed at many sites in Europe. And we've got one station in the southern hemisphere, which is La Réunion. So it's a volcanic island. It's the only southern hemisphere station in ICOS. It's a volcano, so the topography is very difficult to represent for most models. So even at the high resolution, the forecast overestimates the amplitude of the variability at the synoptic scale. There was a large pollution event in January 23, so you can see on the right of the time series. It's probably related to an air mass coming from Austral Africa. And it was captured in the model. And curiously, there is a constant offset of methane in the analysis. Since we are in the southern hemisphere, we can continue or not. Nothing happens. I can't get at the next slide. Yes, thank you. So we can continue in the southern hemisphere with measurements on board the Marion Dufresne. so the French ship. It's a monitoring program with ICOS and the Actris network. There are a lot of instruments on board, which you can see on the right, some picture and their location on the ship. And there are also other species than CO2 and CH4, but I will focus on these two here. It's a project for 4 years, so there are several cruises. So you can see on the left maps some cruises from 2020 to 22, and we've got CO2 and CH4. And the objective would be to ask for long-term support. And you can see there are the maps on the top. On the bottom, it's results for CH4 and CO2 over several cruises. So there are about 10 cruises already. So here are the details of cruises in 22. So February, March, and April, May. With CO2 on the top and CH4 on the bottom every time. And you've got the, on the time series, you've got the observation in blue and the simulation in black. There is an issue with the latitudinal gradient of methane in the area, with a gradient actually in the simulation, which is not seen in the observations. And when you go really south to the subantarctic front of CO2, it's well represented. There is an example on the 14th of February where it was the cruise was going in these latitudes. When we look at the pollutant peaks, so like I said before, there are pollutant peaks due to air masses coming from Africa. Once again, there is a good phasing in time, but it's overestimated for CO2 and underestimated for methane. So we probably relate these to surface emissions, and in this area, it's very probably the biomass burning sector which is dominant and which may have an issue. And so this was in the surface, so now let's go on the vertical. So this is what we do at Trenou in France. It's air core profile, so on the left you've got the picture with the balloon, and the payload is still in the hand of my colleague. So on the top left you've got all the profiles, all the vertical profiles, all the air cores for the 4 species, including H2O. And on the bottom you've got the maps of the trajectories. So we can't, Trenou is on the southeast of Paris, and we can't do air cores when there is a possibility that they may go over Paris, over the Paris area. So that's why the trajectories are all on the southeast. This is an example of the profiles we get. So on the top, the measurements with CO2, CH4, and CO for two air cores in September 20, on the 15th and on the 10th. And on the bottom, you've got the CAMS high resolution forecast to compare. There is something strange with CO above 18 kilometers. So I let this for CO people. So this is an example of what we got this year, so 22 till last month, no, till March 23. So you can see, so each panel is the model in blue, observation in orange, and on the right, the difference between observation and model, and you can see we've got very high resolution information on the vertical. So this is for CO2, and we've got the same for methane. So of course, once again, the situation is very different for the two species. If we put all the data together, so that's what you got on the left for CO2 and the right for methane. So we've got the mean over all the profiles for the model on the left, the observation on the middle, and the difference, observation minus model on the right. There is an overestimation of the increase of CO2 from the surface to 23 kilometers, so it's going from 2 to 4 ppb, it's overestimated. And in CH4, we've got an underestimation in the troposphere, and then we've got an overestimation of the gradient in the stratosphere, which is, I think, quite usual for a lot of models. But it's quite a big point because it's for up to 200 ppb at the top at 23 kilometers. So to stay on the vertical, we've also got IAGOS data. So on the left, you've got the vertical profiles, which are mainly at Frankfurt Airport. So CO2 on the top, CH4 on the bottom. And on the right, you've got the comparisons when the planes are at the cruise level. For CO2, there is an overestimation, about 1%. And for CH4, there is an underestimation. The issue with IAGOS is that they are the instrument issue, so we don't have measurements since the spring of 22, so a bit more than 1 year now. And after this in-situ data, we've got the remote sensing data. So on the left, you've got the NDAC network columns. On the right, the TCON. So you've got the stations from the north to the south again, and it's still the difference between the model and the observations. And it's 2 weekly resolution this time. So like before, the whiter the color, the better the agreements between observation and data. So this is what we've done this year. What we want to do is also working on the greenhouse gas reanalysis rerun, EG4. I don't know if you say EG4 or EGG4. And what we are currently working on is experiment I1DG and the control run I1X Edge, which will restart from 2018. So we'll target October 2018 to March 19. And it's ongoing, but very soon to be delivered. At the beginning of July. And we'll compare the old EG4, the rerun, with the same set of observation. So IAGOS, NDAC, and TCON, but without the IAGOS data, which are missing over this period. Thank you.
Okay, thank you. So thanks, Isabel. So yeah, a lot of new measurements for validating the greenhouse gases. But any questions, I think leave them for the lunch break, please. And we move on to the next presentation, which is online with Philippe Sillet from CAR, talking about carbon tracker for CAMS. And so Philippe, over to you.
Good morning. Thank you very much. So I'm very pleased to present the first near real-time daily CO2 emission product that we put together for the CO2 MVS and different service elements for CAMS. This is now supported as part of the CAMS 51A Carbon Monitor project. So the motivation for producing low latency emission is mainly due to the fact that official CO2 emission inventories reported by countries are lagging behind time because it takes time to collect energy and fuel data. The situation is that all the Kyoto countries are doing a report with a 2-year lag compared to the current year. And the non-Annex 1 countries, which together globally emit more than 70% of global emissions, have an even longer delay. Some countries have made the latest communication 2 years ago, others 5 and even 10 years ago. Our research is coming from a collaboration between Tsinghua University in China, California University Irvine, and our department at LSCE. We started this project motivated by the COVID period because at the time we had no idea of how much emissions were changing for greenhouse gases and pollutants. So we decided to develop basically a new approach. This approach considers emissions on a daily basis based on activity data. We do collect a large number of unique activity data, such as daily to hourly power productions from national infrastructures and even individual utilities. This data set now covers 70% of the worldwide power production. We also collect activity data related to the industry output and the production indices, data down to the individual location and types of aircraft and ships. And based on that, we build empirical models that are essentially calibrated on the annual total CO2 emissions reported by all the different nations in the year 2019, but we give it a temporality for 6 sectors: aviation, residential, shipping, transportation, and power. Of course, this is a glimpse of the data we collect, such as the aviation flight radar 24 data, power data, congestion and traffic information from TomTom for more than 500 cities in the globe. And more recently, for Europe and the United States, we have collected and processed daily pipeline delivery of natural gas to the industry, to the power sector, and to the residential sector, which helps us a lot to understand how buildings, commercial and residential buildings, respond to temperature changes in winter by using more gas. It's a large data set. We log on the different websites providing data once a day. We have collected so far more than 15 million of individual entries. There is an automatic pre-processing module completed by a manual QA, QC, and finally a module which is calculating emissions. In the case of the power sector, it's a simple product of the power produced by each type of power plant and its emission factor. So this is so we started the project in March 2020. We have reanalyzed the data starting from January 1st, 2019. It is up to date now, up to the end of January 2023. The data are daily per country. You can see the very large and long duration drop of emissions related to the COVID confinement in particular, but also the rapid rebound in 2021. Also, some countries like India were still strongly affected. The regrowth of emission again, in particular during the summer period due to hot summer conditions in Europe and China in 22, and the situation where we are in 23, with emissions so far being similar to the previous year, with large regional differences, in particular a surge of emission from China during the first quarter of 2023 by up to 4%, but a decrease in other regions. The data are only updated up to the last month. Also, we collect power and traffic data on a real-time basis. Some of the other data, like aircraft position or industry output, are not available on a daily basis. That's why we deliver the total emissions with a 1 month lag. But for specific sectors, we could do that on an actual near real-time basis. More recently, last week, we have published a specific analysis which improved the calculations for all EU 27 countries and the UK. You can see the development of emissions and the share of different sectors. The emission profile look good, but it's important to evaluate them. We evaluated them against the classical annual inventory, but also to get information about the temporality quality against preliminary national communications and a few other data products. We are aware of improvements, such as the use of Eurostat monthly fuel data, which unfortunately are not updated frequently enough for us, and the ENSO gas consumption data, which are daily with a low latency. Validation is important. So you see three columns on the figure. The first one is for each quarter of the year 2019. The difference between our CAMS 51A carbon monitor estimate of emission in the dark color and some nice preliminary emission bulletins, which are produced in some European countries, France, Netherlands, UK, Germany, and Sweden. So you can see that we have quite a good agreement for the quarterly average values of our daily emissions when compared to these countries' energy data, which are completely independent. In the second column, you can see the change. The change is a smaller signal, but during the large disruption of the COVID period in 2020, we do have a very good agreement with the national estimations, I would say within 5% for the magnitude of the drop. However, for the recent period, the situation comes back to a more normal mode. And if you look at the change in the last quarter of the year between 21 and 23, we see differences that appear of up to 5%. It's not catastrophic. It's even larger than 5% for the Netherlands. But it means that when you have a kind of more normal regime, even though there is, the Ukraine crisis and energy crisis in Europe at the moment, uncertainties on a product based on activity data, assuming constant emission factors like the product we have, become a bit larger when you are monitoring small signals, hence the number of improvements that I have explained before. We also worked with the EDGAR team to transform those daily national estimates into global maps. This product is called GraySed. It is fully accessible. It consists of daily 10-kilometer maps for 10 sectors, for 6 sectors, which are based on the EDGAR sectorial spatial activity maps and blended with the TROPOMI NO2 satellite data, regarding subnational changes of activity. And those products have been transformed into emissions of daily NO2 and CO for calculating the change of atmospheric chemical composition related to the recent changes in the methane budget that we published in Nature last year. To summarize, we have been relatively successful at publishing the result and analysis of the results in a number of publications. We are at more than 30 peer-reviewed publications over the last 3 years, including some in Nature Communication and Nature Climate Change. We have an annual brief in Nature Communication for Earth and Environment. All the data are publicly available. They are gracefully supported now in Europe by the Copernicus service, CAMS. And I just want to conclude with the products that we have, to be clear from the website. If you look at it, we have global daily CO2 emissions for 36 countries and the rest of the world. We have a similar product for China, but at the level of individual provinces with regional data, at the level of individual states for the United States. We have new power production data for all the different power sectors, including those that do not emit CO2 for 130 countries. I was contacted by C3S because these data have no equivalent in terms of coverage and resolution. We now provide country-level estimate for the European Union and the UK. We have these global gridded maps for CO2, and we are working on a global near real-time gridded map of methane emissions based on other type of information like extraction and location of sources of methane. And finally, we have been also working with the cities network and we provided an evaluated estimate of annual and daily CO2 emissions for 1,300 cities in the world. Unfortunately, very few cities in the Grand South, but the comparison with, let's say, city or high-resolution inventories in other countries for those cities show that uncertainty on the order of 10 to 15% for annual CO2 budget. Thank you very much for your attention.
Okay. So thank you, Philippe, for very informative. We're almost back on schedule. The next talk is a summary of results from COCO 2, which Richard England's going to give. So please.
Yes, thanks. I'm not Anna. Anna wasn't feeling entirely well today, so I'll try to go through this. Just one comment on what Philippe just presented. The carbon monitor graphics will be available on the CAMS website, hopefully within the next month or so. So watch that space. All the nice illustrations of the activity data-based emissions can be accessed through the CAMS website. I'll go through COCO 2. COCO 2 has been one of the main projects to really develop prototype systems for this whole new CO2 monitoring and verification support capacity within CAMS. So there's been a lot of activity. I can talk for hours about this. I only have 12 minutes, I think, so I'll have to go through it very quickly. The presentation will be available anyway after the meeting, but we also had a nice presentation day at the end of last year. And those presentations are available on the COCO 2 website itself if you're interested in more details. So start with the aim of COCO 2 and the consortium. We have a really nice group of institutes together within the project, bringing together lots of expertise that we have available in Europe. And as I said, the main aim is to really develop the prototype systems for this new surface element within CAMS. We had the SHAPE project before COCO 2, which was more scoping. What do we need to do? What are the basic ideas? COCO 2 is trying to develop this, implement this, test what works, what doesn't work, where do we need more development, because we can't expect when we're pushing the science so much that everything will work instantly. So there's a lot of work going on in COCO 2, and I'll just try to give a brief overview of all this. This diagram is basically the same one as I presented in my introduction earlier, a little bit less colorful, but it's the same building blocks. And all I want to show here is that within COCO 2, we try to address all these different building blocks through the different work packages. So on the observations, on the prior information, on the integration, on the output, and also on the what we call decision support team, transferring data into policy relevant information. So this has all been done in COCO 2 to make sure we cover all the aspects. So starting with work package 2, which is on the prior and ancillary information, a lot of work has been going on here, complementing what's already been done in CAMS as part of the operational service, because obviously we have contracts on emissions, but this is more explorative and supporting also all the experimentation we need to do in the COCO 2 project. So on global scale, on regional scale, and also very important, trying to estimate the uncertainty in these emissions, because if we want to provide products in the end with uncertainties, we need to cover all the different elements of the system. So this has been addressed as well. And not just the anthropogenic emissions, biosphere fluxes, ocean fluxes, everything is being looked at within the project. Another really nice development within this work package is on the global point source database, trying to get a better definition of the various point sources around the globe for CO2, make sure they're in the right location, that we have the best information available on the emissions from these point sources, have an idea of the uncertainties, and then also how they behave over time, so try to get temporal information. And the temporal information is important if you look at the graphic on the bottom right. Whoops. Oh, it's not showing it here. Sorry. There's a bar with the Sentinel-5P overpass time, which is just 1 moment per day. And in order to interpret the emissions throughout the day, if you just have one instant snapshot, you want to have information about the temporal profile of these emissions. So this is important information to interpret satellite data as best as we can. Going to work package 3, which is on the global development. So this is very much focused on the IFS, but supported by some of the other systems that we have available in Europe. I can't go through all the details here, but working hard on improving all the different parts of the carbon cycle, bringing together all the fluxes inputs. And in order to test these, we have been carrying out and are still carrying out nature runs. So we run the IFS at high resolution for a year and try to evaluate it as best as we can, and then try to see how the different developments hopefully improve the fit to the observations. So there's just a few examples shown here for CO2, where we have, for instance, improved the LAI climatology, showing a better fit to the observations. For methane here on the bottom, where we have been working on the wetlands, and again, trying to get the better fit to the observations. So it's really development, test, evaluate, and further development. It's all part of the cycle here. Now it doesn't. Oh, sorry. Yeah. Also within this work package, development on the data simulation aspects or inverse modeling aspects. This has been mostly focused so far on methane, because there we have the satellite observations through Sentinel-5P. And methane is also easier to capture with what we currently have developed, which is what we call a short window 40 configuration. We look at the observations within a 24 period, while for CO2 we think we need to extend this. And to this extension, and I'm not going into detail for that, is the work currently being done, trying to see how we can gather as much information about the emissions from the satellites to make sure we have a good constraint on the emissions. For methane, it's a little bit easier than that. So there we have been testing it and producing results, comparing with other studies to make sure we do something that's sensible. Also, a very nice development is using the IFS data simulation system to estimate uncertainties through an ensemble of data simulation, where we can perturb the different inputs, the observations, but also the emissions and other parts of the system, so we can have a better idea of the uncertainties of the products coming out. But we can also actually reverse this to some extent and use it as an observation simulation experiment. So we have simulated observations through this EDA system, where we basically sample the basic run of the ensemble, and then use the perturbations to then go backwards and get an idea of the uncertainty reduction if we would have observations of a certain quality. So this has just been developed and is being tested. It is working, it's technically working, and now we need to really see how we can apply this to simulated observations. Within COCO2, we already have, together with EUMETSAT, we have developed a data set of CO2M simulated observations. So this is one of the key inputs there to see, well, what will these satellites contribute to the system. Then going to the next work package 4, which is focused on the local to regional scale. Very much focused on CO2. Methane has been less prominent within COCO2, but there's other activities doing similar things for methane. For CO2, there's been a lot of development trying to find clever algorithms that can detect the plumes, which are not always easily visible. There's potentially a lot of noise. The signal is low, so we need to have a good filter to pick out these plumes. We can also bring in other information like NO2, which is a much clearer signal. So how do we combine these observations and make sure we have a good plume detection, which we can then use to estimate the emissions of the plumes. So this is a lot of development, basically preparing for CO2M when we get these observations. On the national scale, a bit similar, trying to further improve these inverse modeling systems, compare the different systems we have and learn from the differences. A bit similar to what we do for the CAMS regional air quality forecasts, where we have an ensemble to not just have a better medium, but also to learn from each other. Where do we do well, where do we do not so well? Yeah, and this is an example. This is actually coming out of work package 5, which is focused, among other things, on addressing uncertainties and how do we cope with these. So this is an example of where we brought together methane inverse model studies from different groups and looked at the difference between the models. And what we see from this is that models don't agree as well as we would like them to be. So we have to look at why is this happening? Why can't we have a better agreement between the models? And what can we do to improve the system? So this is really important. We still now have the time to test things, to further develop things before we go operational in several years' time. So we are exploiting this information that we have available within the community. I'm running out of time, so I'll speed up a little bit. Work package on observations, work package 7, which has been looking both at what is available in terms of, especially in situ observations, what are the gaps, are there new technological developments that we can benefit from, so writing different reports, also classifying observations in terms of required timeliness, things like that. So there's several nice reports. But another component is where we actually have done, in a few locations, we have done specific observation studies where we make the measurements and try to better understand, for instance, emissions in a city environment and what it looks like and what we need to take into account when we do all the data dissemination inverse modeling studies. Then work package 6, which I skipped, but there we have been bringing together the results coming out of the project of the different work packages, also interacting with what we already do in CAMS. And one key element from this in the last year was this submission to the global stocktake that I mentioned before. So we have described several data sets that we thought were mature enough for this exercise, providing good documentation, also good description of what we think is the accuracy, what is the value, focusing again on different aspects, global and local skills. So this has also been a key output from the project. And then the final one is on the what we call the decision support tool, where we really are thinking how do we translate all this data into policy relevant information. So several activities within this work package, bringing together different estimates and trying to see, well, how do we present this? Here we also worked together, for instance, with the Verify project that has now finished, but they did a lot of work in presenting results in a nice way. And in COCO2 we're trying to see, well, is this sufficient or do we need to further improve things as well? So here again, different reports coming out of the project, and we now are going through a feedback exercise where we have described what we think would be useful, but we have shared this with inventory agencies, with DG Klima, for instance, and different groups, and try to get feedback about usefulness of what we think we could do and try to adapt where necessary. And that's all I had to present. Thank you very much.
Okay, thanks, Richard. So again, we'll move on to the last talk before lunch. This is Ernest Coffey, who's going to talk about, he has a question about what COSO will provide for CAMS.
Good morning from the last talk. We will see most of the slide will be more or less the same thing. Then yes, it's about the COSO project, which is a follow-up of the CO2 COCO project that which I presented recently. I show this just to remind you what we are doing. In fact, we are trying to do something which is about the integration system, which is based on inverse modeling technique, which use observation from satellite, from in situ, in order to do the system itself, and also from the prior information that there. And this system, once it's built, it's also built around the atmospheric transport model and also a non-surface model. And we need to improve all this piece of information to have a good system. I don't want to go into detail. Just to give you an idea about where we are, as Richard already said, we are not coming from the scratch. We have through experience research project which will feed this project itself. Then we are somewhere, I don't know how we use it. Then the project is somewhere, you see it, and the objective is to feed the CO2 MVS at the end. Then just to tell you about the activity that will be inside of CORSO, what are the main partners of this project? It's about 16 partners. The contribution from the European Commission is about 5 million euros. And also, as already said, we are not using all these projects to improve the CM2 FVS system. There are projects that come from the greenhouse gases, also from atmospheric pollutants, to feed this project. Now, what are the aim of CORSO? First, CORSO to improve the estimate of the emission factor. This has been also addressed in COCO 2. Also to see if we can use the information that comes from the local emission estimate by using the observation. I will go after that on about that, to better estimate the anthropogenic emissions, and also to further analyze the added value of the carbon-14 and APO meaning by atmospheric potential oxygen observation as a threshold to separate between the anthropogenic emission and the biosphere emissions. And also to have an improved land surface model, because as we want to have the anthropogenic emission from this system, we need to disentangle between the anthropogenic and the biosphere emissions. And also then to provide some specific recommendation to CO2 MVS. And to reach this objective, there are 4 main science work packages in addition to the coordinations. Then we have the own package which consists to improve the estimate of emission factor and ratio. And the second one is to benefit from the co-emitted there, considering the NOx and CO, to see how we can use this species, because there will be measure in the CO2M to improve the separation between the anthropogenic and the biogenic emissions. And most importantly is how to use the carbon-14s and EPU observation to disentangle between the anthropogenic emissions and the biosphere emissions. And also to use the satellite data in order to improve the characterization of the land surface model, like concern the surface model and also the vegetation models, in fact. And if we want to go, we want to highlight some important topic in this project. For instance, as Richard already said, if you are measuring the hotspot at one time, you can have some information about what time, and then if you want to have, for instance, the annual total, and in some day you miss this information from, for instance, for the CO2, we have a chance to have this information from the NA2, and then if you have a ratio, you can have the information, give you some information there. Then how do we measure temporally varying emission with temporal sparse observation? Then we need to have a synergy between some species in order to improve the system. The second thing is, if you have a possibility to have, in COCO 2, they are developing a tool which allows to have a hotspot based on mathematically simple things, how do you say, a budget method. And then if you have a hotspot, how you can improve your system globally by using this information from there. Then if you have this information, for instance, for the emission, you can firstly compare to your prior to see if there are some differences, or also how you feed the system by improving your prior emission in order to have a good optimized emission at the end. And some very interesting thing is already to say is how to consider the carbon-14 and the APO in order to disentangle, as I said, to separate anthropogenic and also biogenic emissions. Just to tell you what is about 14C carbon. It's a species created naturally by the cosmic ray in reaction with nitrogen. And for instance, if you have a material which takes this one, and the half-time of this component of species about, I think, is about 5,700 years. And then for the fossil fuel, if they took it for the year, the last more than this half-time, in the atmosphere, they will be free. And if there is a fossil fuel somewhere, there is no carbon-14 inside. This is theoretically what it is, but in reality, I think in 1955 until 80s, there is an open experience of nuclear things, then this contaminates this observation. And also when you have power plant, nuclear power plant, you can have this contamination. Then, okay, the thing is to look at how this component can help to disentangle between the biogenic fluxes and the anthropogenic fluxes. The PO is completely different. It's a conjoint measurement of the concentration of the CO2 and also for the oxygen. And from these two components, you have a tracer which is insensitive of the photosynthetic component of the fluxes are insensitive to this tracer. And then from there, you can have an idea about what then you see somewhere you have the concentration of CO2. They vary differently. We have the CO2 increasing, the O2 decreasing, and the tracer is in below. And then you can derive the fluxes from there. This has been done experimentally at some site. Then the idea in Corso is to use the global and regional model in order to simulate these fluxes and then to see the concentration of the atmosphere by using some observation there and then verify if the model are good enough in order to take some information from there. And the last topic, which is very important, again, I'm coming with the same thing. We want to have anthropogenic emission with the system. Then, in the atmosphere, when you have the concentration, is integrated concentration, you cannot see which is anthropogenic, which is coming from the biosphere. Then you need to have a land surface model, which is clearly good in order to have, because so far, something you have to say is the land surface model, the fluxes they are producing. When I'm talking about the fluxes for CO2, that concerns, for instance, the gross primary productivity, the photosynthesis part. Then, in this part of the project, the idea is to use, for the land surface, to use satellite data based on the several polarized indexes to see how the model variable sees this satellite component. And then the first study based on neural network, which is we compared and we modeled variable, for instance, the LI, the GPP, and so on with the satellite product concerning this quantity, which is the ratio there. And here we have a matrix. Then you have for different components, the soil moisture, the soil temperature, the brightness of temperature. Then we see that what we expect, for instance, if you consider the soil moisture and the soil moisture seen by the satellite, we see a very large negative correlation, which is expected, and then so on. And then work is going on. And because, in fact, so far, the land surface model, we use a simple equation which comes from empirical measurement. And the second part concerns the solar-induced fluorescence, which measured by the troposphs. There, normally, what we want to see with GPP, the gross primary productivity, is using SIF, which is a proxy information from GPP, due to the fact that the fluorescence, which is a signal emitted from the lift. There is a link between the two things which come from the what we call the parameter which determine the rate of the photosynthesis at lift area. Then what you see, for instance, concerning the GPP simulated by the SVA model from Meteo France, we see a very good correlation between the two things. Then the idea is to assimilate this data in order to improve the model. I think this is quite so. Yeah.
So thanks, Ernest. So this now concludes the greenhouse gas session. I think it's time for lunch, and we reconvene here 1:30 for the final session. Sorry? 1:30 sharp. This is coming from Vincent Henry, so please adhere to this. Thank you. And thanks to the speakers again. Thanks.
Pronto, pronto? Prova. Yeah. Okay, like this. Okay, so yeah, it's 1:30, so we can begin. Okay, yeah. Please come, take a seat. We need to start. Okay. Coming back after lunch as always. Okay, so yeah, we can start with the last session of this CAMS General Assembly. So let me first introduce myself. My name is Isabella Mazza, and I'm the head of Program Contract Management team at CNWF. So, as you may know, 70% of the budget that we receive from the European Commission, it's managed and outsourced to third parties. And the contract that we signed with our contractors are critical business tools which allow us to set and achieve clear results, which of course make CAMS a user-driven operational service, as you know. So I just want to provide you a little bit of numbers, because as of today, under the second phase of Copernicus, we have signed 35 CAMS and joint services contracts, which actually reflects an engagement of almost 100 entities, so private and public, so from all over Europe. So it's a truly European effort. Yeah, and. So I actually would like to thank in specific Anita, Julia, Kevin, and Angeliki, who in my team are managing the CAMS contracts, and of course all of you who are making this service a success, of course. So it has been great to see, of course, the progress in presented at the GA in all these last days. So now, without further ado, let's start with this last session of the CAMS GA, which is focused on CAMS interfaces. With the users, of course, at all level, and with the overall landscape of connected activities. So as first speakers, we have, I'm inviting Karen Oregon from CNWF and Thomas Popp from DLR on the stage to present us the CAMS users and who are they and what are their needs.
Yep.
Over to you.
Yeah, so hi everyone, welcome back. I hope you enjoyed your final lunch here in Valencia. So just to quickly introduce our presentation, I'll provide a quick overview of the current state of CAMS user statistics, so a bit of a numbers game like Isabella just said, and we will showcase how we identify and report these CAMS users, and then Thomas will explain how CAMS is enhancing our intelligence on our user base through interaction sessions and workshops. So just to start off then, so in the top corner you can see the headline statistics of our CAMS users. So to date, up to the end of Q1, so not quite up to date, but yeah, so we have 28,875 users of CAMS data sets across all of our interfaces. So that includes the ADS policies and from our contractors as well. And we've got 3,000 active users of CAMS during Q1, so it's a very active user-driven service, so keep up the good work. It's the users who really drive this service, so we like to see high numbers, so continue to do so. And then we've got 240 terabytes of data that has been delivered in 2022, so there's lots of interesting science happening behind those numbers, so it's just to point out how active the service is. So, and also just to note that the total users has increased by 7% since the last quarter, so it's really up and coming. So, the top right graph shows the new and cumulative total users that are registered on the ADS. So it's showing steady growth since our records go back to 2020. But at the end of March 2023, we had 14,230 users on the ADS. So again, really active service. Yeah, so just how do we characterize our users? It really helps us to drive the service if we know where our users are and who we need to keep targeting. So we just break down our users by geographical region. Is kind of one of the easiest ways to do so. So the map that is shown here just focuses on our European users, but obviously there are users globally, so mainly in China and the US are the next top users outside of Europe. But you can see from the table and from the map that the top 10 users in Europe, with France, Germany and the UK being the front runners. Yeah. So just for the next slide then, just to break down the statistics a little bit further geographically. The top left graph shows the evolution of our European users of CAMS over the last year. So France remains in the lead with the highest number of CAMS users, and they've not been getting much competition, so hopefully we can drive a little bit of friendly competition to see can they be overtaken, but we'll see in the next GA if those numbers change. And unfortunately, I will just point out that Italy has overtaken Spain in the last year for a number of users, so hopefully we'll get more Spanish users engaged in the service. Don't mean to put you on the spot, but that's, the numbers say what they say. Just one thing that I wanted to touch on that's not indicated in the slide is usually when we report on user bases and stuff, we tend to focus on the top users. And sometimes this is unfair because it doesn't represent kind of the work that's being done in maybe the smaller countries. So I just wanted to briefly stress the importance of our user interaction workshops. So I will take the example of Bulgaria. They had a user interaction workshop last September. And since that workshop, we've seen an increase of about 18% of our Bulgarian users, which is one of the highest percentage increases over the last couple of quarters. So it just really shows the importance of that interaction that we do have with different user groups to really engage them in the service. So just note that Bulgaria is now in the beginning stages of the National Collaboration Programme for CAMS. So this will only increase their user base further, and I think Christina will explain more about the NCP in her presentation later on and how it engages users. So then just quickly moving on to the CAMS datasets. So of the 14 datasets that we host on the ADS, the top 3 can be seen in this table. So the top three are regional air quality, global fire emissions, and the global reanalysis data sets. So this is just to point out the amount of data that has been downloaded in the past year. So it just helps us to understand the products that our users are most interested in and how we can continue to engage those users. And then just finally, another point for this slide is we've recently launched an updated CAMS user satisfaction survey, which you can access by scanning the QR code, or you can find the link to the survey on the ADS homepage or in the CAMS user forum. So this survey collects voluntary feedback from the users, and you provide a score of 1 to 5 of how satisfied you are with the CAMS service. So hopefully we get 5s all the time. It's not always the case. As you can see in Q1 2023, we got a satisfaction survey score of 86.4%. So we're always striving to do better, but we can't do that without your feedback. So if you could please fill out the survey and let us know of any requirements that you may need or knowledge gaps that are in the service, and we'll try to incorporate it into our user requirements database, and just to make sure that, if possible, that we can cover all of your requirements. So yeah, the user satisfaction survey is open every quarter, so it's not open continuously, but we do promote it. So just look out on the ADS or on Twitter and fill out the survey if you have any feedback. So then just next slide then. So I'll just quickly go through this slide as well. So it gives an overview of the evolution of our reporting on CAMS users and how it will change over the coming months. So I think Luke will discuss later in his talk how the ADS and the CDS will be merged into the CADS by the end of 2023. So with this comes some changes to the registration process. So we'll be collecting more statistics on our users to hopefully increase our knowledge on our user base and drive the service towards what the users really need. So yeah, you can see from this slide that there's a list of user categorizations that are required under COP2. So the ones that are in red are new categorizations that we've not yet reported on, but these will be included in the new registration process for the CADS. So we'll discover more information about affiliation and thematic activities that our users are working on. And then there's also some changes to the existing categorizations. So there's just a bit of homogenization of the different statistics that we'll need to report in the coming months, but you don't need to really know all the details of how we implement that. But just the bottom line is that we're slightly changing how we collect our statistics to help us better define our user base and inform our user intelligent activities throughout COP2. So with that, I will pass on to Thomas to talk about these user activities.
Thank you, Karen. So I will now give you a few glimpses of what we do to increase intelligence of CAMS about its users and for its users. I have 3 more minutes, but a bit more slides, so I will try to touch very briefly on everything. So we are here to not only collect the technical requirements, but to really understand the motivation and the needs of users. I want to acknowledge the team who is working with me on this, and of course with all CAMS contracts. So what we have upgraded in this contract from the predecessor contracts is what we call now a CAMS user interaction session. So this is a sequence where we work with the National User Forum. We do a series of interviews or survey. Then we do an online workshop. And we also have a concluding wash-up meeting where we really try to take stock so that the national collaboration program of CAMS, but also the national agenda can be fed with what we have learned from this interaction session. And we do this in a strategic way, so we have criteria to select the countries, like commitment or a different mix of countries and their needs. We use a generic template for these interviews so that we can do the analysis in a structured way. We just had the third one of these user interaction sessions, the user workshop 2 days ago here in Valencia for Spain. And in the end, there's a report public on the CAMS website that contains all the findings. This is the map of all the user workshops without interviews that have been happened since Promote and MEC and CAMS. And you see a good European coverage. Those in yellow, I hope you can see them in the bottom, are those 3 ones on the current contract, which had also this preparatory interview phase where we were able to get into more depth. So we were in Bulgaria, in Denmark, and in Spain. And one of the major outcomes of these user interaction sessions is try to depict graphically the value chains, to understand who has to work together, which elements are coming from CAMS and from other sources. And I have now one example for each of the 3 countries. So for Bulgaria, we have here an example that the City of Sofia Council staff, they use the CAMS source apportionment tool on their smartphones in case of episodes as a complementary information to understand what's happening on a short term. And of course, this tool is not optimized for working on a mobile, but this is the kind of application that is really happening with CAMS. For Denmark, the situation is, every country is different. And for Denmark, for example, we have it that there is a well-established value chain to do the air quality forecasting in the country. And there are now discussions which added value can come from CAMS. Which of the pieces can be replaced by CAMS, and where is really the added value? So there is an evaluation planned in the NCP to really understand the possible benefit on emissions, on temporal profiles of emissions, on using the long-range transport information from satellite, things like that. And for Spain, we have a different situation again. They have their own forecasting modeling system, but they also use the blue CAMS part to drive the probabilistic information to be able to do EPS grams for 700, for even 900 locations in the meantime. A deficit that was mentioned here is it's not available for the Canary Islands, which are part of Spain and need to be covered. And also it's not ready to use for Twitter, so they want end-user friendly material sometimes. Yeah. What's happening now? Yeah, okay. For Spain, the situation is that, no, I lost my thread. They are also discussing what can be replaced with CAMS. So if you compare this global and European model could be done by using CAMS. And again, they have to analyze where is the benefit and where is the added value. Good. An element that we have been doing for many years now is collecting systematically and analyzing systematically user requirements, judging their feasibility, their needed effort, and their potential impact. So there is a database with more than 600 user requirements, which can be a group of several technical specifications. And here is just a collection out of the last year. There are many more, but just to give you an idea, there are technical, like data download quarter, there are concerning training, there are many concerning new elements like the air control toolbox, new functionalities, but also higher resolution in other parts of the world, like the Ensemble for Europe, or another element on the radiation service doing forecasting. And finally, I want to conclude with some thoughts and findings out of the 3 initial user interaction sessions that we have done so far. So understanding how dust exceedances can be discounted from the reporting is a very important activity for many countries. Therefore, this initiative by Leonor is very relevant. Before countries are willing to replace elements in the country by CAMS parts, they want to see the proof of the added value. And here the NCP is an important element. Complementary information by the policy tools is appreciated. We have seen a good cross benefit between the NCP and this user intelligence service. And regarding the CO2 MVS service, here is an opportunity for co-design, because knowledge on the countries is not as large still as it could be, but there is a lot of experience that should be brought in to really create user-friendly products out of this service. And yes, here is the graphical animation that Karen has introduced, showing for Bulgaria the timeline. After the workshop, we have a substantial increase. So it's worth doing this, and I thank all involved here in Spain and in the other countries for engaging on this. It's free time that is put in from the member states, and we hope that we can help the CAMS service to evolve towards the user needs. Thank you.
Thank you, Karen and Thomas. Any burning question for them? Eleanor.
Thank you. I think it's very impressive to see how the activity of users is improving. So I have two questions, in fact. The first one is, it's been very interesting to see that many of the users in Europe, they are also contractors, which is it's a good part. But now we are beginning to see a part that is not only contractors, that we are having different users that are not in the community. Are you planning to have some way of distinguishing between contractors and new users, especially to see now the evolution of this? Because I think we will begin seeing a boom on those that are not contractors because of the activities that have been carried out. So that's the first part. Are you planning to trace this in Europe? And the other is that I see a very stable Asia interest. And I would like to know who are the interested, if you know anything about this Asian interest.
Oh. So from my perspective, I don't want to stand in front of the speaker. To answer your first question, for the reporting that we do, so it's just really a numbers game that we report the statistics to the European Commission, but it's a really interesting point that you've brought up. Maybe it's something that we should look into to kind of disentangle the contracted users from the rest of the users of CAMS data. But yeah, so maybe we can report on that in the future. It'll need some investigation, but it's a great point that you've brought up. And then for the Asian users, it kind of stabilized due to kind of the DHS move that ECMWF performed last year. Some of those users were lost in our reporting, but we're working on getting those users back. But yeah, I don't know if Thomas wants to add.
If I can add to the first question, Leonor, I think we have some 100 or 200 contractors involved and close to 3,000 active users in a quarter. So it cannot be that it's mostly contractors. There is, of course, an active element, visible element by the contractors, but by numbers there are others, companies and authorities and everyone. Yeah.
Thank you. Okay, so I can invite the second speaker, Micha Ratzinger from ECMWF, who will talk us through CAMS' new web charts.
Thanks, Isabella. Yes. Yeah, so I would like to discuss a little bit the improvements we've been doing on the field of publishing CAMS web products. And what I mean by web products are graphical products that we publish on the website on regular basis. So it's something based on CAMS datasets and updated on daily or less frequent basis. So Karen mentioned that we delivered 240 terabytes of data in the first quarter. So why are we even talking about that? Aren't we supposed to deliver data and that's it? We should give the users then the freedom to do whatever they want. So, and here are a few reasons why maybe it's not completely futile activity. So first of all, we want to show what we do before before users have to download anything. So giving demonstrations, what we do, like a illustration of the products, so they get a feel of what we provide. Then maybe second also important point is that maybe what is the information available on graphical products is enough for certain users, which I think is true in many cases. And then maybe also is that some users also don't have the skills, and they're perfectly happy with what the information they can extract from the published results. But also then some other points is that we also like to have these products at hand. When there is an episode, we would like to be able to quickly analyze it to see how our operational systems perform during that time. So, and maybe the last point is that some products are quite complicated, so it's not maybe straightforward for users to replicate them. That's it. So we are migrating all the web production to a new ISNWF chart publishing system, which was developed initially for ISNWF open data and open charts catalog. But during the development, we were quite heavily involved in discussions with the developers, so our requirements were taken into account, and we're happy to see them implemented. And yeah, more recently, also all the kind of ISNWF internal charts are using this system. So yeah, why we are doing this? Why we're doing the migration to the new system? So at the moment, we have two main publishing platforms. So one is hosted at Meteo France, and the other one was at ISNWF, and they are both kind of legacy software, kind of difficult to maintain, end of life. So we want to switch those off. Then the second point is that we want to harmonize methods, how we publish these products between different production systems. So it's another benefit. And then I'll show later a little bit about the architecture of this system. So and hopefully you can maybe appreciate that this kind of prototyping and development of new products should be easier and faster in this new system. And based on these requirements that we were able to provide, we have many more functionalities that were not available before. And yeah, hopefully because it's used, the system is used for ISNWF operational services. It's quite well maintained, monitored, and scalable as well. So in cases we have big spikes of demand, we can cope with it. Yeah, just a very quick schema of the system, how it works. So we have a data layer on the top left. So anything to do with the input data is stored and indexed there. So it can be grid data, it can be some point data, or it can be also the pre-generated graphics already developed. Then in the top middle, it's a computing layer. So it's a bit of computing resources to, first of all, to retrieve data and then do some kind of aggregation, post-processing, unit conversion, or maybe one of the applications hopefully will be compute-derived quantities like air quality index. That should be perfectly feasible. And then on the right-hand side, there are just some auxiliary databases which are needed, for all the configuration needed to generate a given graphical product. And then we have a rendering layer where the actual graphical products are created. So very quickly about the functionalities. So maybe first one is this kind of composability. It means that we can link together different products. So we have a map, and we can link it to an action, that what happens when you click at a given location, and we are able to generate time series plot for that, and that was quite often required functionality, and that's now available. I mentioned that there are a lot of possible input streams to this system, so it's quite flexible. You could extend it. We have this computing. We cache everything. Maybe I skipped it on the previous slide, but we cache everything. So everything is most of the things is generated dynamically. So some things are maybe expensive to produce. So we want to cache things that we don't repeat the same expensive post-processing steps, for example. So then one kind of nice new feature is this chart set function, which try to demonstrate on the top chart on the left side is you can kind of align two different completely independent products which share some common navigational dimensions, and then you can navigate through these common dimensions together. So like I try to show here an example showing PM and fire analysis plots side by side, and maybe see some patterns. Sharing. So Thomas mentioned a requirement from Spain that they would like to be able to refer. Users would like to refer to a plot, so this will now be possible. So you can generate a permalink to a given product, and you can share it, and the products will stay static for a period of time. One also quite important new feature is that the products are embeddable. What it means is that they can be packaged in a very small piece of HTML code, which can be then embedded in any kind of remote website, and we are using it already a lot, and there has been a lot of requests already before, so I think it's quite a popular functionality, and then a few others. So we'll have scripting access to everything as well. So we started with migration of CAMS global forecast products, forecast and analysis products, and we completed this migration in March. Not much for users. Not much has changed. At the first glance, there are all these new kind of features, but the people who are familiar with the system should be able to use it and maybe explore the new functionality. And then the first kind of a real example of this embed feature is we published some UV index viewer on the EA Health and Climate Observatory portal last year. And then the next step now is the migration of all the regional production, which is at the moment still hosted at Meteo France. There was this nice report produced a few years ago by Angelica and Augustin, and there were quite a lot of studies and recommendations on that. So we took this as a input, and the first kind of the step towards this is that we produce some more data viewers for this Health and Climate Observatory portal for just a limited set of species, and quite a simplified setup. So just assemble just one model around, so make it as simple as possible. And we are close to publishing this and announcing it on their website. And then the a bit more kind of bigger task is then actually completing all the migration of the air quality production, and that's been ongoing. It's kind of ran in parallel a little bit with the work we did for EA, but we need to finalize. There is a link to the kind of prototype, so if you want to have a quick look, but hopefully we can get something ready by September. And then just a quick last slide is, where we are going, what is kind of maybe the future. So we have, CAMS website and Atmosphere Data Store, which are now quite independent, separated, and you can get charts from website and data from Atmosphere Data Store. And we would like to make this boundary a little bit softer. So we want the users to be able to get, both plots and maybe also some data from the website, like point-based data. That we get a lot of requests for that. So with this new system, this will be possible, and there is like an OGC API standard for this, which I think we'll implement. And then the other way around, so the green arrow is that we also want to introduce more methods to visualize data on the ADS. So using things like Jupyter notebooks and some kind of more kind of tailored data set interactive explorers, something also that we are working on. So, and that's it.
Thank you very much. Any question?
Just precision for the last slide. Will you publish the APIs and I saw that you have a Climate Lab Python library, so it will be something of the same way. So it would allow somebody actually to publish his own maps, getting the data from the data store and publish whatever, something which is not already existing?
Exactly, it's a generation. So you would get an API where you can request raw data in a bit nicer interface and subsetting as well.
With the advantage of keeping the same look and feel than the one from ECMWF.
That's the purpose of these Jupyter notebooks. Yeah.
Thank you. Thank you, Miha. Yeah. Okay, so our next speaker is Luke Jones from ECMWF, who will talk us about updates on CAMS data access.
Hi, so yeah, I'm going to be talking about the ADS, which you've already heard mentioned many times, but I'm going to pretend nobody's mentioned it yet and take it right from the very beginning. So it stands for the CAMS Atmosphere Data Store. It was launched in June 2020. And prior to the ADS, there was no single place where a user could go to find all the CAMS data, which made life a bit difficult for users. But now with the ADS, there's one place that has access, that gives you access to almost all of the CAMS data. It's called the data store, but it doesn't necessarily store all the data. Some data is stored within the ADS, but some data is stored externally by other providers. Some data is even calculated on demand. But all of that complexity is hidden from the users behind a nice, common, homogenized interface, so they don't have to worry about that. It's free and open, but you do need to register because we need to have you accept licenses, and we need to monitor usage and ensure that there's a fair service provided to all people. And it's very easy to use. There's websites that you can go to. You can select the data set that you're interested in. And then you get a web form with various menus and checkboxes. You select the fields that you're interested in, and then you can see there's a screenshot here in the bottom left corner, and you just click Submit Form, and you'll get a download through your browser. Or alternatively, you can click on a button, and it will show you a little snippet of Python, which uses the CDS API, which is the Python interface, Python API to the ADS, and shows you the equivalent request in Python. So then you can build that into a non-interactive workflow if you want. We have 13 datasets currently published on the ADS, which you can see listed here, 4 of which are near real-time, updating every day or even multiple times every day in some situations. And the rest are historic. They still get updated with new versions, but not every day. I say 13 plus 1 datasets. The plus 1 refers to a hidden copy of the global forecast dataset, hidden in the sense that it doesn't have a record on the website, but you can access it through the API, through this dataset name here. And that allows you to test your workflows with the eSuite, 48R1 eSuite, which is going to become the operational model on 27th of June. So that allows you to download the 3 new parameters that 48R1 produces, glyoxal and biogenic and anthropogenic secondary organic aerosol. But the important thing, if you're using GRIB format data, is that the GRIB field encoding will change on the 27th of June. It's different in 48R1. It uses a more advanced compression algorithm, so your GRIB data will be smaller. But if you're not using a very up-to-date version of EC codes, you will not be able to decode the GRIB. So if you have an automated workflow using GRIB format, using the global forecast, it may well break on the 27th of June, so it's very important that you test your workflow. And you can find more about this on this link here. We have some other updates coming. We have the second half of the global reanalysis coming soon on the ADS for 2022. And I was going to tell you that all of 2022 for the regional reanalysis, the interim reanalysis, was coming soon, but I was told about 2 hours ago, actually it was done today, so that's more gone recently than coming soon. And we have 3 more data sets also coming soon. Firstly, the European air quality point forecasts, otherwise known as the MOS-corrected regional forecast, which you heard about from Météo France earlier yesterday or the day before. Erroneously listed here as historic. It's not historic, it's near real time. That will update every day in line with the gridded regional forecast. And that's going to be published very, very soon, maybe in 2 weeks or something. We're just working through a final few usability issues. There's going to be a gridded version of the solar radiation dataset published soon, hopefully this summer, I think. And we're also hoping to publish the regional emissions relatively soon. A bit of usage information. I hadn't realized you would all already have received a lot of usage information from Karen. So some of this is the same information again, but we have 15,000 registered users on the ADS from almost 200 countries. About 1,000 active users. My definition of active was the past 30 days as opposed to Karen's past quarter, so it's a bit of a lower number. And the ADS satisfies about 50,000 requests every day, which equates to about 1.5 terabytes of data. And as Karen said, the most popular, the most active countries are European countries and China, but they are spread all over. The US is a big user. About 2/3 are academic, about 10% public sector, 10% private sector. And I've listed the datasets here in order of popularity as measured. Differently to Karen, I've measured this in terms of by number of requests in a given week. And by this measure, the global forecast and the regional forecast come out top, which wasn't surprising to me. What was a bit more surprising was that only about a quarter of the requests for the global forecast are for the near real-time forecast. So there seems to be strong interest in the historic forecasts, possibly because of the gap between the end of the global reanalysis and the current day, and users are using the forecast to fill in that gap. So I'm going to talk a bit about the future of the ADS, but I can't really talk about the future of the ADS without talking about the CDS, which you probably know about, but if you don't, the CDS is the Climate Data Store. It is to the Copernicus Climate Change Service what the ADS is to CAMS. So it's the single one-stop shop for C3S data. And it's essentially a parallel system to the ADS. It uses the same code base. It's running on the same cloud hardware. It uses the same storage, but it's a completely separate instance in terms of virtual machines, in terms of its dataset catalog and its user registration. So you can't use your CDS account on the ADS and vice versa. And it's a lot bigger. It has more than 10 times the number of registered users, more than 10 times the number of data sets, and it delivers more than 50 times the amount of data per day, I think most of which is the very popular ERA 5 reanalysis. So the ADS and the CDS have been very successful, but software standards, technologies, best practices have moved on a lot since they were first developed. And we also have learned a lot of lessons from the first implementation. We'd never built anything like this before. So now both the ADS and the CDS are undergoing a full rewrite from the ground up, using the most modern technologies and best practices and all the lessons that we've learned. And the biggest change, which users don't necessarily have to worry about, but under the hood, the CDS and the ADS will now be one system. There will be one set of virtual machines, one merged catalog, one user login, and this combined system we're calling CADS 2.0. But this is, CAD stands for Climate and Atmosphere Data Store, but this is more of a sort of internal project name. It's not something which will be very visible to the users, because we still want the ADS and the CDS to maintain their respective identities and their respective brandings, and we don't want the users to see the merging of the catalogs. So there will be two external portals to the single system, and these will be the same URLs that you currently use for the ADS or the CDS. And your entry point will determine the section of the catalog that is visible to you, and it will determine the branding that appears on the website and the licenses that you have to accept, etc. So to all intents and purposes, from a user perspective, this will still be two separate systems, but from our perspective, this will be a single system which will really help with maintainability and resource management. It won't be totally transparent to users. One big change is that there will no longer be separate ADS and CDS accounts. You will use your ECMWF account to log into both the ADS and the CDS. If you don't already have an ECMWF account, you'll have to create one. And the existing ADS and CDS accounts will be retired once the old system is retired. Done something very interesting with my fonts. That is not the font I chose for CDS API and CADS API. I preferred mine. So yes, the CDS API, like every other part of the system, is being rewritten, and that's now going to be renamed the CADS API. So we are leaking that CADS terminology a little bit. This won't represent too much of a change for existing users, because the data download, your requests will still be the same. You won't have to change your requests, but there will be new functionality. One nice thing will be that you will be able to programmatically query the catalog through the API. So you will be able to give it a partial request and then ask it to give you all the possible completions, the valid completions of that request. So you'll be able to ask what dates are available for these variables, what variables are available for these dates, which will hopefully be very useful to users, especially for near real-time data sets when you want to know, has the latest forecast been published yet? It will have better error messages. We'll be able to communicate better with the users through the API. And we're hoping it will have many more post-processing options beyond what we already offer, which is really just area subselection and format conversion. So we're hoping for spatial meaning, temporal meaning, ways to reduce the amount of data that you have to download. But this isn't guaranteed yet. It's still very much a work in progress, and it's not clear what we're going to be offering there. So we are planning a beta release for Q1 2024, is what I was told. I think somebody else, Karen was told end of 2023, but I think that's slipped now, but it's not totally clear. But we won't be switching off the old system immediately. There'll be at least a 6-month transition period where the old CDS and ADS will continue operating to give users time to transfer to the new system and give us time to iron out any problems. So if you know the CDS, if you've used the CDS, you might be familiar with the CDS toolbox, which is something that was never implemented on the ADS, and it's the part of the system which is going to change the most for users. The plan was to replace it with something called CADS Toolkit, which was going to be a Python toolkit which you could run in a Jupyter Lab session on the CDS, or you could independently download and install locally to be able to use it on your own system. But at the same time, ECMWF was developing something very similar for our use, sort of general Python processing and visualization package. And it was realized that the overlap between the two was so extensive, it really made no sense to have a separate CADS toolkit. So now there would just be one thing called EarthKit. It's not necessarily CDS, ADS specific, but it's going to have very good interoperability with the CDS and the ADS. So it's a new open source Python project. It's going to be built on top of the kind of community packages that you may already be very familiar with if you use Python, Xarray, Pandas, NumPy, Matplotlib. It's going to come bundled with the necessary ECMWF code, such as EC codes. And the aim of this package is very much to simplify data access processing and visualization for the user, to remove as much of the tedious boilerplate code you have to do in order to do things which for you seem very simple but turn out to be quite complex in Python. And it's intended to be very familiar. If you're already familiar with these packages, these community Python packages, you should be instantaneously feel at home with EarthKit. It's going to be hopefully very fast. It's intended to make use of best use of parallel environments, so multi-threading, multi-processing, very scalable. It might be quite a chunky download because it comes with these ECMWF binaries. So it's going to be installable as 4 separate sub-packages. EarthKit data is the part you will use for I/O, and that's the part which will be able to read from the CDS and the ADS. And that's actually already been released. You can see more about it on this link. Maps will be used for plotting, regrid for interpolation, and then also processing. And yeah, EarthKit data is already released, and the others are hopefully coming soon in the following months, certainly months rather than years. And this is just a quick example, or a couple of examples to show how easy it will be to use. So on the left, you can see a 3-line, or 3-statement, I suppose, download and visualization from the CDS. So you import EarthKit, you can give it a CDS request. Note, I haven't had to separately import the CDS API because it's all bundled together. In a single line, you can download an ERA5 reanalysis field, and then with another single line, you can make a very nice plot with contours, color bar, descriptive title. I don't know how many lines of matplotlib you would need to make that exact plot, but you certainly couldn't do it in a single line. So it's showing how easy this is intended to make life for you. And on the right, again, in the interesting font, you can see how easy it will be to convert to and from the EarthKit data objects that you get when you read data, and the more familiar types of objects you might be more familiar with, such as Xarray data frames, Xarray datasets, Pandas data frames, NumPy arrays. You'll be able to convert easily between the two. So that's it. The ADS has been a great success, but it continues to evolve, hopefully in ways you will find useful.
Thank you, Luke. So we are a bit tight with the time, but maybe we have time for a very quick question. Is there any?
Thanks very much. And I understand the need to express, when you want to express things in how many downloads or how many terabytes or something. So I'm from the CAMS emissions project, and I just want to make a remark that, for example, it struck me that there was like 150,000 for the global forecasts or something, and 160 for the global emission product. But then we also need to know that the global emission product is like, on the ADS, is like 2 versions behind. So all the people that use that actually get it through another way. So it's important that with these things we also still keep in mind what is behind the. I don't want to. I understand, that it's difficult to. I just want to not have these things lead their own life on. How important is it that these things are updated?
I think it definitely.
That's the only comment, right?
No, you can measure popularity in terms of number of requests. You can measure it. You'll get a totally different result if you measure it in terms of terabytes downloaded. Neither of those necessarily represent importance. There's no real way you can represent importance. So yeah, they're to be taken with a pinch of salt. They're to give you a sort of flavor of usage, but yes, not to be confused with importance.
Okay, thank you, Luke. So our next speaker is Cristina Nanasso from ECMWF, who will update us on the CAMS National Collaboration Program and the synthesis of the first Atmosphere User Forum.
Thank you.
So good afternoon. I try to be quick, but I'm very glad to be here and to present the National Collaboration Program again, because this wording is around since a while now. Last year we presented the plan and the very first action. Now we can start presenting some of the very first outcome of this program. This presentation is shared together with Julie and Julia that are working with me on this very interesting and challenging program. But also, it's really a collaborative effort from a lot of other colleagues at ECMWF. Only to tell you that, as you know, the National Collaboration Program is an integral part of the CAMS infrastructure, so it's really inside the service, and is the interface toward the user, to represent also a new approach that the Commission was asked us, and the idea is to really work together with the countries, with the member state and contributing state, and to develop with them some joint activities. And this is represented by this Rubik's Cube that underline the new approach that we are trying to have toward our user. The three sides of the cube represent the services that are up and running now since a while. The thematic apps that focus on some specific categories of user, and then the National Collaboration Program that really focus toward the core user at a national level. The main goal of the CAMS NCP is really to enhance the uptake of the CAMS product at a national level, co-designing some of these activities together with the countries. Under the program, there are several projects, one project for each country, for each interested country, and it's important to see this as a two-way process. So there is CAMS that is continuing to provide the products, the expertise, the support, and also the communication part, the information to the more general public. On the other side, with this project, we are asking to our contractor, in this case, to really uptake and reinforce the use of the products at national and even regional level to fulfill their mandates, to assess the quality of the product, so to give us some feedback, because for us it's very important to receive user feedback to improve the service. To strengthen the coupling between CAMS product and existing national products, if any, and also to provide a new gateway to reach the general public at national level, where the language now is a key element. Each project is unique, so we create a modular approach for the program, because each country should select the work package or the modules that respond, that fill to their national needs. Here we reported the list of the work package that we have identified 1 year and a half ago now. All of them are optional. Only one is mandatory, and is the communication work package, because we really think that communication is a key element to get closer to the user. Some additional info more on the contractual part. Now we have procurement contracts, but the idea is to pass to grants in the close future, I hope. The duration of this first phase is of 18 months. And the allocated budget for the entire program is around 16 million that is going to cover till the end of the current multi-annual financial framework, so till the end of 2027. An overview of the timeline. Everything started, let's say, in November 2021, when we formally introduced and presented the NCP to the Copernicus User Forum. Then we started to interact with the member state through a survey that we distributed, and that was only, let's say, a tool to start a direct dialogue with the core user in each country. In March-May 2022, we started a discussion with the first 4 pilots, 4 countries that proposed themselves to start to be pilot for the entire program. We had the first meeting in April with 14 countries. Then we started with the signature of different contracts. Now the process is really ongoing with all the other countries in a different step, but we are really trying to reach out all the 29 countries, 27 plus 2 contributing countries, Norway and Iceland. The first, we had 2 days ago the first meeting of the NCP, and we start calling this meeting the Atmosphere User Forum. So far we are engaged and we are in contact with 27 countries. As you can see from the different color, there are different phases of the process. With 9 countries, we have signed the contracts, and with the other, we start, let's say, the first meeting, the first interaction, and the first exchanges. This is only to give you an idea of the first meeting that we had. We tried to really present the NCP to the member state to give them the possibility to discuss about the first action, the first discussion that we had with all of them. So we organized the agenda, focusing on the different work package and on the different module. The objective of the meeting was really to present the status of the NCP, to discuss the ongoing activities with the countries, to exchange, so to give the possibility to the countries to exchange between them, but also with ECMWF and with the expert at ECMWF that can provide support and responses. The idea was also to collect the feedback from the country and maybe emerging needs or additional needs, and to discuss with them on how to better respond to their needs. I think that was, let's say, a successful meeting. On site, there were 39 attendees coming from different countries, obviously, and also online there were 34 people. And the discussion was interesting, a lot of exchange, and also requests of clarification, let's say. The idea is to have this kind of meeting, recurrent meeting every 6 months, so one online and one in person during the General Assembly, but also we would like to organize ad hoc meeting for different modules and addressing different issues inside the program. So some outcome from the subsession. I took this nice picture from Chris' presentation, because from 2 ideas, we can have a better idea. So communication is a particular case because it's mandatory. So we really force the country to reflect and to act on communication. But also we gave them the possibility to propose whatever they want, let's say. So we were quite flexible in accepting different kind of communication activities. Because also we recognize that at national level there are very different contexts. And also the first discussion that we had with the ongoing contracts really reflect these heterogeneity at national level. Then we had a session on training. The goal of the training is really to equip new and existing CAMS users with the necessary skill and knowledge to make the best use of CAM products and services. And then we put on the stage an example or a use case coming from Italy in this case, where they presented a very interesting approach, collecting requirements from their user, and then design some very well identified and very well defined, let's say, activities and training session for their specific user communities. Then we have the other three more scientific modules. The first one is the direct use of a CAMS product. The idea here is really to improve the interaction with the user and to co-design some parameters that can be of interest in a specific country. The use case here is from Poland, so they have identified end user, and they are really focusing in responding to these national user and to their need. Coming from Poland, there is really the willing to collaborate with other NCP group, and this is also a very interesting request, let's say, coming from their side. Then there is their quality downscaling. We know that several countries have their own official national air quality forecast to support decision makers, but only few of them use CAMS as a boundary condition. So the idea is really to support them in better use CAMS product for this specific action. The final goal is really to have a composite map of Europe composed of high-resolution maps coming from all the countries. And this example is coming from Ineris, representing France for this use case. The last one is on emission. So also in this case, it's the use case is from Norway. They have identified a clear user need, and for them is road dust emission. And also an existing gap, because they recognize that these emissions are underestimated. So they identify the end user at national level, and they propose a solution using their model, but also CAMS in this case. We are going to have a new CAMS NCP website under the atmosphere, under the CAMS website, the main page. The idea here is really to report the contribution coming from the member state. The first example that I have here is for Italy, but we are collecting the input from the countries, and we are going to create this website, and it will be online soon. So general outcomes from these first 18 months, from, let's say, ECMWF perspective, it's a learning process. It's a learning process for us at ECMWF, but also for the countries. So it was a very constructive dialogue with all the countries and with all the actors involved. I think that we are in a good state, and there is a great willingness of member states to participate. As I mentioned before, the budget is fixed, but we did our best, and we do our best to be flexible as much as possible in time and in the objectives. We also ask and force a little bit the member state to see this project not as, let's say, a research project that is going to finish in 1 or 2 years, but to reflect since the beginning on the impact that this project should have on their national system. And this is really one deliverable of the contract. There is a close interest of the Commission, in particular DG DEFIS, but also of the other entrusted entities that they started after our initial proposal to develop a similar collaboration scheme. On our side, we are doing to develop something similar also for C3S. And then the other goal of all this process is really to create a community of experts that can discuss on our products, on the CAMS product, but from the national perspective. Expectation from the countryside. They really would like to see this as a long-term action, because this allows them to set up some internal action that really are recognized as important for their institution, let's say. They really want to know from us, so from the service, the future plan of the service itself, because in this case they can prepare their own service or their own institution to follow what we are doing. This is also to avoid duplication. And also the other important aspect that they want to bring their knowledge from the national level to the European level, so to CAMS. It's very important for them to discuss with the other countries of their topics, but also to have this kind of transnational approach. And also another element that they recognize very important is to the co-design and the co-development of some national services. With this, I thank you all the involved countries. I want to thank all the colleagues, in particular Julie and Julia that work with me, but also the other department, procurement, contract, and communication. And looking forward to all the 29 signed contract.
Thank you. Thank you, Cristina. Is there any burning question for Cristina? No? Looks like not. Thank you, Cristina, again. Okay, so our next speakers are Vincent Puck from ICNWF and Anne-Caroline Lange from the ULIC Research Center. Over to you. Who will take us about Destiny and activities connected to CAMS.
Yes, so to finish the General Assembly, a bit difficult exercise for me, which is to talk about Destiny. So you've heard about Destiny or Destination Earth quite a lot already, and colleagues of Destiny have another meeting this week, so that's why they are not here. And I think it's the right time to present a little bit more in more detail Destination Earth to the CAMS community, because as you will see, there are lots of synergies possible between the two programs. So first of all, Destination Earth is under DG Connect, which is a close relative or brother or sister of DG DEFI under the same commissioner. The implementation of Destination Earth is shared between three interested entities: the European Space Agency, ESA, EUMETSAT, and ICNWF. And of course, in ICNWF, being interested entities for both Destination Earth and Copernicus puts us, as well as ESA and EUMETSAT, in a right way to seize those synergies. So Destination Earth is, first of all, a very ambitious program. So maybe you've read some documentation about it. If you look at all the ambitions, it's probably very frightening because it's, first of all, it sits like Copernicus under the EU Green Deal, the need to accelerate a transition, the need to support mitigation and adaptation through better modeling, and I would say the main visible aspect of Destination Earth rotates around the concept of a digital model of the Earth So this concept comes from industry. The idea is to have a digital model that is accurate enough, representative enough, so that you can test policies. And that the other aspect of Destination Earth, which is with possible synergies with Copernicus, is that it's not only crunching big numbers on high-performance computer, but it's also developing new ways for the user to interact with policy and to see what policy could have what impact. Destination Earth, as I said, started just a bit over a year ago. In ECMWF, the director of Destiny is Irena Sandu. She succeeded to Peter Bauer, who is retiring these days. And Destiny, unlike Copernicus, is organized in phase of about a bit over 2 years. Gradually developing, you see the objective of phase 3, a full digital replica of the Earth. So we are now in the last part, starting the last part last year of the first phase, which is to develop 3 elements. ESA is developing the core service platform through which the users will interact. EUMETSAT is developing the so-called data lake, which will host all the data produced by Destination Earth, but also by Copernicus and other sources of data. And ECMWF works on developing a digital twin engine and digital twins, and there are other slides on that. Phase 2 will follow to further enhance this system, probably integrate more of the digital twins, and demonstrate some services. So the role of ECMWF in Destiny, it's focusing on 3 things. A key thing is to develop this digital twin engine, which allows to run systems, digital twins, on high-performance computing. And there is a close connection of Destination Earth being under DG Connect with EuroHPC, which is the federation of high-performing computer in Europe. So to make sure that these applications can run in the different places. In Spain, there is the Barcelona Supercomputing Center, which will have a pre-exascale computer. In Germany, Finland, etc. So making it work on the latest high-performance computing facilities available in Europe. And then the development of 2 digital twins. One is focusing on extremes, weather extremes, and there will be some more information about that. And the other one focusing more on climate modeling and climate change adaptation. So climate change adaptation, the first digital twin, it's supporting the understanding of the impacts of climate change. And the idea is really to help better define mitigation and adaptation strategies. So there, typically, it's looking at simulation that cover several decades, looking at resolution of 5 kilometers. So it's a lot more refined than the models that run for the IPCC at the global level. Within a regional level, it's more commensurate, but it's a big step change for that. And it's covering atmosphere, land surface, sea, ice, and ocean. So it's, I would say, IPCC IR6 on steroid, this digital twin. And it must have some quality, because the idea is that not only the academic community can run this, or the team developing this system can run this. Ideally, others can work on it. The other one is numerical weather forecasting, global numerical forecasting on steroids as well. So looking at the short to medium range, 2 to 5 days, very high resolution, so aiming for up to 1 kilometer global, and I will show you where we stand in this in this direction. Same, the Earth system approach, but also having some configurable elements to cover certain application area where adaptation or mitigation measure can be embedded as a model element. And again, something that needs to be robust and not just for the expert developing the system. The idea behind Destiny is that
through more realistic models representing processes at a resolution that are closer to what's in reality, it will be possible to do better simulation. There are many ways, many possibilities why they could be better and more realistic, in particular to be able to use more of the data that is available, that today maybe is not used because it's too fine resolution for global models, maybe because the global models don't have certain aspect of vegetation or other system well enough represented. And it needs to be interactive and configurable to respond to very specific aspects. So this illustration that to finish this introduction, it's to show you that it's underway. So we are well into the first phase, still 1 year to go. This is a comparison of Hurricane Irma from 2017 from the US geostationary. You see this eye of the cyclone, and you see how it is seen by ECMWF high resolution of today. Reasonable, well placed, but the eye of the cyclone is way far from reality. We've been able to run, not at 1 kilometer, but 1.5 kilometer. In this case, I think it was on a US computer, waiting for the European capacity to build up. And what you see is a much better representation of the system, in particular the low pressure, but also if you look in detail of the system. So there is lots of potential to do better with this increase. Destiny, as I said, is not only doing the better global system, it's also about making sure that these twins, these facilities will be useful for the users. And as in Copernicus, there is an element of use cases to see how application can leverage from what will be developed. It's a bit difficult because Destiny is developing, and at the same time, so there are no pure Destiny products, but at the same time, it's very important to engage early enough to see what these higher resolution, better, more comprehensive system will be able to contribute in a range of domains, including air quality. And that's where is the link with CAMS very closely. So there are a number of use cases that have been that are funded under the digital twins. For extremes, there is a big portfolio of activity looking at different aspects: hydrology, renewable energy, and air quality. And now I will give the floor to Anne-Caroline, who is leading one of these use cases dealing with air quality.
Okay, thank you very much, Marc-Henri. So I'm going to present our use case on air quality. So it's a group of two working groups at Forschungszentrum Jülich. One is really the group which is also participating in the regional CAMS, and the other one is more on machine learning applications for air quality at the Jülich Supercomputing Center. And when we read the call for these use cases for Destination Earth, we thought so they are really building up on new meteorology. So as we all know that meteorology is highly coupled with air quality, it would be interesting to see the impact of the high resolution meteorology on our air quality forecast. And therefore we decided to develop an on-demand system for our users. So mainly, I would say in the beginning environmental agency, but it can develop in general to other users. So we want to develop an on-demand system which provides air quality forecasts or analysis depending on the needs of the users, and which can be directly, producing forecasts and analysis. So in the phase 1 of Destination Earth, we are collaborating closely with the German environmental agency UBA and the environmental agency of the Land North Rhine-Westphalia. So such that we need really the needs of the users. So here I would like to shortly present our envisioned system. You can see the core design part of Destination Earth, so the Destination Earth user platform, the data lake, and the digital twins on the right-hand side. And what we will build around it or in it, in this system, is a user interface. So this is the connection point for our users so that they can initialize air quality forecasts. Then it will be able to provide like very quick insights. So this will be the machine learning forecasts at the position of the measurement site. So measurement data will be learned and later on provide quick forecasts. Then we will have a containerized version of EuRAD-IM, which provides like air quality forecasts kind of in the way as we do it in the CAMS service. To give the user also the possibility to evaluate what policy making can do, for example, in terms of emission mitigation strategies. We will also include an ensemble system of the EuRAD-IM where the emissions will be perturbed and we will have different results for different emission scenarios. And finally, we also included a machine learning downscaling tool. So as long as the digital twins are not available on the very high resolution, we will use the machine learning downscaling to downscale the EuRAD-IM output on a higher resolution. And what is the last very important part for this Destination Earth use case is that we really provide products which can be directly used from our users. So the visualization or like data provision is a final very important step. This is now giving you a short insight on the current status of our use case. So we are currently working on the containerization of EuRAD-IM such that it can be installed on Lumi. On top of this, we are now trying to get rid of our intermediate WRF meteorological driving system for our model, so directly running EuRAD-IM on the basis of IFS and later on the digital twin output. And besides of this, we are also working on the downscaling part. As I said in the beginning, the high resolution won't be available, but we want to provide high resolution forecasting, and therefore we will use the machine learning part. And this gives insight to this. So we have a long year procedure of running our model from a European scale nested down to a very local scale here. It's North Rhine-Westphalia on a 1 kilometer resolution, and we will use this long time series to learn a deep neural network to downscale the information from European to local scale. And so far, we have experience with this downscaling for temperature variables from ERA 5, and we are now transforming this to the main atmospheric composition species being included in the model. And this is finally a small insight into the forecasting with machine learning at the position of the measurement site. So also here, so far we experienced very good performance for forecasting ozone at the locations. Of course, it's not directly comparable with CAMS level forecast due to the representativeness, having like really point observations. We want to also adapt all this to other air pollutants. And with this, I would like to close, and I would like to take the chance to make you aware of the next second Destination Earth user exchange meeting, which will take place 13th and 14th of November. This year in Bonn, and I think it's a good opportunity for everyone who's interested to see not only the applications for air quality, but also for energy systems, for heat islands, forestry, and so on. So it is open to everyone interested in the activities of Destination Earth. Thank you very much.
Thank you, Dansari and Anne-Caroline. Is there any question from the audience on Destiny?
Yes, it's not totally clear to me, so I have a very stupid question for Vincent Henry. Is it the plan at ECMWF to evolve IFS into the atmosphere component of a digital twin?
It's too early to respond. What is clear is that there are synergies between NWP, Destiny, and Copernicus. How far all the technical aspects, of course, forecasts need to happen on a timescale which is very short. So there are lots of complications. In the end, I think, yes, that's the vision. How far it can go, what is the lifetime of Destination Earth is funded by tranche. Just like Copernicus after 2028, we don't know. ECMWF forecast will be there for sure for our member states. So there are all these aspects. But what is clear is that Destination Earth in particular in terms of portability of codes, and Caroline was showing progress being made with EuroDM, it will help a lot currently. Our system works on our Bologna thing. It took a lot of effort from colleagues to port it to US or Japan. And it's taking a lot of effort now to move to European nodes of the Euro HPC. But the vision is to consolidate. It's not just to make a project to use some European Commission money and forget about it. Yes, in the end, the idea is that the system used for numerical weather prediction should be more realistic. Whether high resolution brings benefit for the forecast, or we could invest in, I don't know, bigger ensemble members or things, still remains to be seen. So I would say it's upstream of what you're mentioning.
Thanks.
Any other question? No? Okay, thank you again, Anne-Caroline. And so let me invite to the stage Maria Berdal from the DG Defis and Vincent Rippeuk from ECMWF for the closing remarks. Thank you.
Thank you. Hello, good afternoon. I hope you all had a good General Assembly. I know I did. It's good to be here because it's important to meet in person, see the faces behind the contracts, and have discussions that we probably wouldn't have had any other place outside of the coffee breaks. This is not only nice, but pertinent to exchange ideas, get informal feedback, and foster good working relationships. And with the pandemic still fresh in our minds, we probably appreciate it even more. So, on the content side, we've had, during the past few days, updates on both long-standing products and activities in CAMS, the core portfolio, and also on new projects, Horizon projects, to expand the service offer and ramp up new service elements, such as the CO2 MVS. The babies in Vincent Henry's presentation of the CAMS family, the thematic hubs, and the National Collaboration Program, they must be teenagers now. The scope has really matured over the last year, and the implementation of these elements are well ongoing. With the launch of the Health Hub yesterday, and also the Atmosphere User Forum on Tuesday. In total, from last year to now, I think we see the full scope of CAMS 2.0 really taking place. I mentioned some examples of CAMS information and products in EU policies in my opening speech. And during the General Assembly, we have heard how DG Sante expects to make use of Copernicus Health Hub and the role of EU Earth observation tools in their future work. We have heard examples of how DG Klima already uses Copernicus products and future plans for use of Earth observation, also in their scope. And we've heard how CAMS dust products are worked into the guidelines to follow up the ambient air quality directive. So, in sum, it's good to meet in person once a year. And your work is valued and used in the political domain. CAMS 2.0 is really taking shape and there's a lot to do also in the next year and years to come. Thank you for an excellent General Assembly. Thanks to the organizers, to our local hosts, speakers, and participants, and see you again next year.
Thank you very much, Maria. You're making my job very easy because you captured all the you struck all the notes that I think are very important. What I want to say is a series of thank yous to finish the assembly. I will start with our communications team under David Armstrong, Francesca Fusco. I don't know if she's here. And our contractor from GoPacom, particularly Tom, Chloe, Alexandra, and then for all the AEV technology, also all the team. I think it was a challenge to have good video and good sound in this very nice setting. It's very bright, so there was lots of challenges. Well done to all. I would like to thank Fernando and all the colleagues of AMET for supporting us in making this General Assembly a success. I think I enjoyed it a lot. As I said in the beginning, we have this survey that we would like you very much to fill in to see if my impression of a very nice General Assembly is just because I'm glad that things go well. Please answer the survey. So thanks to Fernando for proposing Valencia in the first place. My other thanks will go to all of you because I think I agree fully with Maria. We're really seeing CAMS 2.0. I think on all the aspects. That's different from where we stood at the end of the first phase of CAMS. It's progressing. Of course, the National Collaboration Program, the Health Hub, and also the CO2 MBS. So there was this session this morning. We see that we are steadily, as a community, getting there from the satellite to the modeling to the research, and we see also the strong input and momentum that these research projects that are now more closely interacted with CAMS benefit, because it means that this research will be able to transition to CAMS within months and not requiring years to be adapted. So the last word is to say thank you to all for your contribution to CAMS. See you next year. We don't know exactly where, but certainly we'll do a General Assembly. Have a safe trip, and we keep in touch in the meantime through the telco. So thank you very much, and see you next year.
Thank you.